a visitor from deep space drifts toward Mars, while our best eyes begin to blink. Its envelope of gas swells beyond expectations, its brightness stutters, and the moment of closest approach aligns with a period when Mars slips into the glare of the Sun from Earth's point of view. An urgent paradox forms. The riskiest hours may arrive right when we see the least. Stay with this story as we follow what we know, what we fear, and what might be quietly unfolding off camera. Mars has endured ancient impacts, global dust storms, and a slow loss of atmosphere. It is a survivor, but a fragile one. The incoming object, a true outsider to our solar system, behaves in ways that do not quite match the textbook comet. Its coma has expanded early and irregularly. Its brightness has surged and faded in fits. Each of these signals would be interesting in isolation. Together they suggest internal stresses, vents that open and close, and jets that shove the nucleus in subtle ways. None of that guarantees danger. It does complicate prediction. Here is the complication that matters most. The geometry of the encounter places Mars near the Sun in our sky during the critical period. That means ground-based telescopes must fight sky brightness and low angles. Some spacecraft will have safe mode constraints when they point near the Sunday radio. Links can be affected by the solar environment. The net effect is a natural observation blackout, just when behavior could change the fastest. The risk does not come from a cinematic collision across empty space. The risk comes from uncertainty, multiplied by a temporary lack of direct data. We begin with what is known. On the current trajectory, a direct hit on Mars is not expected. The closest approach distance is large by impact standards. Planetary defense analysts would call it a safe pass. That statement is important. It sets the baseline. Now we place the unknowns beside it. Interstellar objects have only a short history in our records. Their internal structure, their fracture behavior, and their gas chemistry do not always map to comets raised in the Kuiper belt or Oort cloud. If this nucleus is already stressed, a small torque or a new vent could shed fragments at the wrong time. The parent body could sail on. The fragments would write their own paths. That is the non-impact scenario that animates the rest of our inquiry. There is also the Martian environment to consider. Mars has no global magnetic shield. Its atmosphere is thin. Charged particles from the Sun and from a cometary ion tail can reach regions that would be protected around Earth. Even modest changes in the upper atmosphere can disturb radio links and navigation sensors. Dust on Mars is famously active. Give the system a little push in the wrong season, and you can trigger storms that darken half a planet. These are not apocalyptic claims. They are reminders that small inputs matter more in fragile systems. The close pass we cannot watch in real time also narrows our ability to rule things out quickly. Imagine the scene inside a mission control room. Teams that normally track Mars orbiters and rovers rely on predictable windows. Then the ionosphere becomes variable. Signal-to-noise drops. Instruments do what they should do in uncertainty. They protect themselves. Spacecraft enter safe modes. They wait for cleaner skies and clearer commands. From Earth, that can look like silence. Silence breeds speculation. The antidote is a method. We will outline that method as the series unfolds. A method begins with priors. It remains unlikely that large fragments reach Mars on this pass. It remains plausible that the coma and ion tail raise the background of charged particles near the planet and its orbital assets. It is reasonable to expect short communication hiccups and temporary data gaps if conditions line up in unfortunate ways. Beyond that, there is an important line we will not cross without evidence. Claims about biological contamination, runaway climate shifts, or solar upheaval sit in the speculative tier. If we explore them, we will label them clearly and explain the physical hurdles they must overcome. Now, we build a narrative spine that can carry both curiosity and care. First, the geometry. Distance that sounds comfortable in daily life can be uncomfortable in orbital dynamics if an object begins to shed mass. Second, the medium. Mars is an exposed world. It responds strongly to energy and particles that Earth can shrug off. Third, the lens. We live inside an observation gap during the crucial hours. We must interpolate with caution, then verify once the planet moves out of the Sun's glare. Known versus unknown will be our constant pairing. Each claim will sit in one of those columns, and we will move items only when data supports the move. To keep the story honest, we also acknowledge what success looks like. Success is a quiet pass, a steady set of telemetry from Mars orbiters, and a data package that helps scientists refine models of interstellar comets. If that is the outcome, it will not mean the alarm was misplaced. It will mean the system was tested and held. It will still be a teaching moment. We will have watched a rare kind of visitor skim a vulnerable world during a period of limited visibility. That is a perfect laboratory for lessons about risk literacy. Risk literacy is the real subject beneath the spectacle. The public often encounters space stories as binaries, safe or doomed, hit or miss. Reality lives in gradients. A non-impact encounter can seed a debris environment. A minor uptick in charged particles can create measurable communication issues. A system that looks calm to the eye can still be noisy to a radio. The more we practice reading those gradients, the better prepared we are for the next visitor that does not care about our schedules or our line of sight. As we leave this opening part, hold two images in mind. The first is Mars, small and red, turning through a path that has been stable for eons. The second is a ghostly envelope of gas that unfurls in sunlight, while cameras on Earth squint through glare. In the gap between those images sits the heart of the story. What changes when cause and effect happen where we cannot watch? In the next part, we gather everything we do know, from trajectory solutions to instrument sensitivities. Then we draw the map of our blind spots. That map will guide the rest of this investigation. Begin with the ground that does not move. The track of the visitor has been solved and resolved by multiple teams, using repeated measurements of position against background stars. Those solutions converge on a closest approach that is distant by common language and yet close enough to study. The object is not on a collision course with Mars, and nothing in the nominal geometry points to a direct strike. This is the baseline, the steady floor on which the rest of the story stands. Its motion is hyperbolic relative to the Sun. It will swing through and continue outward, and the known pull of planets and sunlight pressure has been accounted for in the best current models. Next, the body itself. Observers have recorded an unusually vigorous coma, dominated by carbon dioxide, which is consistent with volatile rich material that begins to sublimate at larger heliocentric distances than water ice. That early activity explains why the object appeared more dramatic earlier than many comets born in our own distant reservoirs. Brightness variations have been reported by independent teams. The cadence and amplitude of those surges imply venting episodes or changes in surface illumination as the nucleus rotates. It remains uncertain whether the nucleus is monolithic or a rubble pile held together by weak gravity and cohesive forces. Evidence is limited, but one inference is that the internal structure contains layers of material with different volatilities, which can open and close jets as sunlight migrates across. The surface. Mars, the stage on which this pass will be judged, offers a set of environmental properties that matter for risk framing. The planet has a thin atmosphere, mostly carbon dioxide, and it lacks a global magnetic field. The ionosphere forms and varies under solar influence and responds to charged particle environments. This is why communications with orbiters and surface assets can suffer during periods of intense solar activity or dust-induced charging. The Martian dust cycle is another known. Dust can be lofted by small thermal contrasts, then concede larger storms through feedbacks between heating and circulation. None of these facts predict disaster. They highlight that Mars is a place where small inputs can produce noticeable changes in the upper atmosphere and in radio propagation. Now, the observation window. The encounter overlaps with a period when Mars lies near the Sun in Earth's sky. Telescopes must contend with scattered light and low elevation. Some spacecraft cannot safely point instruments close to the sunday. Deep space antennas can experience solar interference on certain lines of sight. The practical result is a set of days when acquisition of clean, high-cadence data becomes difficult. This is not a conspiracy. It is orbital mechanics and instrument safety. The space science community plans for such gaps, but it means that short-lived developments could be observed with latency, and confirmation can arrive after the fact rather than in real time. When the view clears, data products will fill many of the gaps. Until then, confidence must be tied to what the instruments can actually see. What do we expect to see if everything remains nominal? Mars orbiters continue scheduled passes, relay links to surface assets look routine, and ionospheric indicators stay within familiar ranges. Astronomers record a coma and tail that extend as expected for the current solar distance, perhaps with modest increases as the visitor receives more sunlight. The nucleus stays intact, and the dynamical solution remains stable when new astrometry is added. There may be mild telemetry hiccups in a few windows, and those would be unsurprising given the geometry. There may be small changes in the rate of dust lifting if timing, season, and regional weather align, but those would still sit within Martian variability. What would count as a meaningful deviation without leaping to extremes? One possibility is a fragmentation event that increases the cross-section of active surface area and produces a step change in brightness and coma structure. A competing view suggests that increased activity could come from surface cracking without actual splitting, which still alters jet geometry and could nudge the nucleus slightly. It remains uncertain whether small fragments, if produced, would acquire velocities and directions that intersect the Martian system. The relative distance at closest approach argues against a sudden hail of large debris, yet tiny grains and gas can still influence plasma conditions over extended regions. If such conditions occur, they would likely register first as communication noise, irregularities in charged particle measurements, or transient attitude control adjustments, as star trackers manage scattered light. The method for sorting signal from noise is already familiar to mission teams. Look for multi-instrument agreement across platforms that do not share the same weaknesses. If a relay glitch appears only during low sun angle passes, treat it as geometry. If two orbiters report ionospheric variation while a third sees neutral density changes, treat it as a physical disturbance. If a single camera reports streaks that no other sensor sees, treat it as an imaging artifact or micrometeoroid impact on that instrument. This layered approach does not produce instant answers, but it prevents the most common misreads during periods of partial visibility. There is also a public framing to maintain. Large numbers can be misleading if they lack context. 30 million kilometers reads as far, which it is, and it also sits in the range where subtle comet behavior can still be scientifically interesting. Energy arguments can sound terrifying when expressed in nuclear equivalents, yet the geometry of space shares that energy over vast volumes. The responsible way to speak about potential hazards is to keep the scale of interaction honest. Charged particle populations can disturb radio links without threatening hardware. Dust storms can lower solar power production without signaling planetary collapse. Fragments of 100 meters would be catastrophic if they hit, but the probability landscape for such a direct path on this pass remains small. Every story needs a compass, and ours points to this through line. The pass is real, the blind spot is real, and the physics that could produce secondary effects are also real. The combination does not guarantee drama, it justifies attention. We will proceed with a two-column mindset. Known items in one column, open questions in the other. As new data arrives, pieces will migrate between columns. Until then, we resist the pull of definitive conclusions. In the next part, we translate distance and speed into consequences that human intuition can grasp. Then we examine how perception can turn comfortable margins into concern when a visitor behaves out of family. A number can feel safe because it is big. 30 million kilometers sounds like a moat around a castle. The mind pictures empty space and concludes that nothing from a small icy body can matter across such a gulf. That is a fair first intuition. It is also incomplete. In orbital mechanics, safe or risky is not a single number. Risk is a product of geometry, velocity, timing, and the behavior of material set free from a parent body. The castle moat is not still water. It is a river with currents, eddies, and debris that can drift out of the channel. Begin with speed. Objects on hyperbolic paths carry high relative velocities. Even tiny grains accelerated by sunlight or pulled into complex plasma flows can move fast enough to become relevant for sensors and surfaces. Kinetic energy grows with the square of velocity. A grain that is almost nothing in mass can still score a detector or create a spark of charge on an exposed panel if it arrives fast enough. No one would call that a disaster. It is the kind of nuisance that accumulates, and in the wrong moments, small nuisances combine into operational pauses. This is how distant becomes present for machines that rely on clean optics and quiet fields. Now think about the cone of influence. Imagine the nucleus as a point that sheds material. Jets carve lobes in space. The sun pulls, the solar wind shapes, and light pressure pushes. The result is not a straight tail but a dynamic volume filled with gas and dust at different sizes. Most of that volume never intersects Mars. The fraction that might intersect is small, but it exists, and because Mars lacks a global magnetic shield, changes in charged particle density can reach atmospheric regions where radio waves travel and where orbiters dip for aerobraking studies. A subtle change in electron density shifts how signals refract. You do not need a rock to hit a spacecraft in order to cause a brief loss of lock. Geometry creates second-order effects that feel like magic until you sketch them out. A fragment released days before closest approach does not need to aim directly at Mars in order to matter. A slight sideways push, a vent opening at a different local hour on the rotating nucleus, or a change in spin state can place a cloud of millimeter grains into a plane that Mars will cross later. The parent body continues on a predictable path. The shed material follows a family of paths that are sensitive to small forces. In this regime, prediction becomes a matter of probability fields rather than a single line. Perception often struggles with this kind of risk. Human intuition is good at billiard ball impacts and poor at sparse fields with long tails in their distributions. Long tail in this context is a rare event with non-trivial consequence. Most passes are quiet. A few produce activity spikes that carry real effects at a distance. Good analysis respects both regimes. It treats the baseline as the anchor. It also maps the low probability branches so that teams know what to look for and what to ignore. Energy helps and misleads in equal measure. People want a single conversion, something to compare to familiar experiences. That instinct can create drama where none is warranted. The better approach is to look at coupling. How much of the energy in a particle population couples into the specific system we care about? A radio link cares about phase stability and noise. A camera cares about scattered light and charged streaks across a detector. A solar array cares about accumulated dust and electrostatic charging. The same external environment can be annoying for one instrument and forgettable for another. This is why multi-instrument corroboration matters. It tells you whether the environment has crossed from mildly noisy to operationally significant. Distance also hides a different hazard, the hazard of delayed evidence. A change in the ionosphere can lead to a missed pass. That missed pass delays a planned downlink. The missing data creates a window where people imagine causes that are more dramatic than the physics requires. The way to manage perception is to stack timelines, expected pass times, expected data margins, and expected recovery windows. When a blip fits inside those windows, teams mark it and move on. When a blip exceeds those windows, teams elevate and investigate. Gravitational focusing is another phrase that sounds ominous. In this case, it is modest. At the stated separation, Mars does not pull the nucleus in any meaningful way. However, a small piece released with the right geometry can receive a slight nudge from the planet and still find itself on a different future path. The key is not to imagine a giant hand grabbing objects from millions of kilometers away. The key is to imagine a narrow gateway where a few pebbles can be redirected if they happen to arrive at the exact moment the gate is open. The majority never find the gate. Mars itself adds leverage. Thin air means little atmospheric braking for small bodies. There is less ablative protection than on Earth. This is why fragments on the scale of a city block are always taken seriously in studies of impact risk. For this pass, the geometric case for such fragments reaching the planet remains weak. The larger lesson is about system sensitivity. Because the shield is thin, weaker external inputs create measurable responses. Dust lifting thresholds are lower, radio paths are more easily upset. Cameras saturate when charged streaks cross the field. To balance the scales, we should name the counterpoints plainly. The coma can be large and still pose no hazard to Mars. Brightness surges can occur without fragmentation. Safe modes can be triggered by sun angle constraints rather than environmental disturbances. A lack of public images during conjunction does not imply a cover-up. These statements are as important as any speculative branch. They remind us of the ordinary reasons that space missions sometimes look quiet from the outside. So how does close become dangerous? It often does not, and that is the honest outcome in most encounters. When it does, it is because geometry, timing, and a fragile medium cooperate. A small change in a nucleus leads to a small population of grains. Those grains drift into a region where Mars is sensitive. The effect is local and temporary. It is measured first by instruments that live in the upper atmosphere and in radio channels. It rarely produces a spectacle in visible light. Every 5 parts of this investigation, we pause to restate the through line. We are testing a claim that the most consequential outcome of this pass may be a non-impact disturbance. Geometry and energy tell us why that claim is plausible without insisting that it will happen. In the next part, we enter the factory floor of fragmentation. We will see how vents, spin states, and internal stresses can turn a single body into a field of shrapnel, and how that field travels in ways the eye does not expect. Begin inside the nucleus, where sunlight is only a rumor that seeps down through fractures. Volatiles rest in pockets. Dust blankets hold heat like thin quilts. As the object turns, one face warms and another cools. Ice near the surface sublimates and gas searches for a path out. Where the crust is weak, a jet forms and the nucleus recoils slightly, a tiny thrust that repeats with every rotation. Over days, these impulses can change spin rate and orientation. If the spin increases beyond the strength of the material, the body can begin to deform. It may stretch, it may split. Many comets that looked solid from a distance turned out to be clusters of pieces held together by gravity and weak cohesion. In such a structure, cracks are not defects, they are destiny. Brightness flare is usually our first signal that something under the surface has changed. The physics is simple. Increase active area or expose fresh ice and you release more gas. More gas lifts more dust. More dust reflects more sunlight. A light curve that once rose slowly now jumps. Sometimes this jump comes with a sudden change in coma shape. Jets that once traced delicate fans become tangled. The tail can develop streamers that point at angles that the previous model cannot explain. It remains uncertain whether a single surge means true fragmentation. One possibility is that a crust failed locally without releasing discrete pieces. A competing view suggests that many flares are microfractures that do shed fragments, but most are small and fade into the dust. Population. Distinguishing between these cases requires careful imaging and repeated astrometry to check for changes in the center of light and in the gravitational solution. The mechanics of breakup follow a few recurring routes. Thermal stress can open existing flaws when day, night, temperature swings, fatigue, brittle material. Differential sublimation can undercut a ledge until it collapses. Spin-up from jet torques can push the body toward rotational fission if the period approaches a critical value for the object's density and cohesion. Internal pressure can build in sealed voids and vent catastrophically when a crack links that void to vacuum. None of these routes guarantees large fragments. They do guarantee that a cliff face will shed blocks and that powder will become airborne. In low gravity, even a block the size of a building can float free with a slow shove and never return. Once pieces separate, their lives diverge quickly. The smallest grains feel sunlight as a force. Photons push on them strongly relative to their mass. These grains are steered by radiation pressure and by the electric fields in the plasma around the comet. They are swept into broad tails that photographers love. Millimeter grains still feel these forces, but inertia gives them a longer memory of the direction they were launched. Pebbles and boulders behave more like little comets of their own. They retain the velocity vector they had at the moment of release. Then they receive gentle nudges from outgassing if their surfaces are still active. Over hours, a cloud of fragments stretches into a filament. Over days, the filament becomes a sheet that follows the general path of the parent, but with spreading that depends on size. Observers describe these patterns with families of curves that sort particles by the time and speed of release. You do not need the formal names to grasp the picture. Imagine a slow fireworks display that never explodes, it only breathes. Every fresh breath adds a thin layer to a drifting veil. If a larger piece departs, it sometimes becomes a secondary source. It vents on its own schedule and seeds its own local veil. This can produce multiple centers of activity that mimic a swarm. When telescopes catch these structures, they can back out when and how the shedding happened. The diagnosis is often strongest after the fact, because the geometry of the expanding sheet becomes clearer with distance. A central anxiety in our story is whether fragmentation near closest approach could redirect pieces toward Mars. The geometry argues that most will not. The separation is large, the window is short, and the directions favored by gas dynamics do not point at the planet. Yet a small subset of paths always deserves attention. If a fragment is released with the right tiny velocity in the right plane, gravity can bend its course by a small amount. The effect is usually modest, but it can place pebbles or grains into corridors that Mars will occupy later. Evidence is limited, but one inference is that the sizes of most shed pieces that could plausibly interact with the Martian system on this pass would be small. These would register first as changes in charged particle behavior and in radio propagation, not as visible meteors clawing at the sky. There is also the question of how fragmentation changes the parent body's future. More active surface area means more non-gravitational forces. Jets act like thrusters that are not aligned with the center of mass. Over weeks, this can alter the path by tiny amounts that astrometrists can detect. In rare cases, the change in spin state after a breakup can expose new areas to sunlight and trigger a cascade that continues for many rotations. A minority view holds that some interstellar visitors might have internal structures that are more layered than typical solar system comets, which could make cascades more likely once the first layer peels. This view remains speculative and should be treated as a prompt for observation rather than a prediction. While we watch for the dramatic, we should remember the mundane signatures that matter to mission teams. A star tracker that sees more streaks than usual. A radio link that picks up extra noise near the planet's limb. A particle detector that reports a shift in the mix of ions at a given altitude. None of these alone proves a shrapnel field. Together, across multiple platforms, they can mark the passage of a disturbed plasma environment or a brief crossing of a dusty sheet. That is how a brightness flare becomes an operational note in a control room, not as spectacle, but as a measurable change in the medium. Fragmentation will always tempt story makers to jump to images of cinematic showers and ground-shaking impacts. The responsible version of that story reads the conditions carefully. Distance, timing, composition, and the fragility of the target environment set the stage. The most likely consequence remains a change in the spaces where signals travel and where dust meets thin air. If the nucleus stays mostly intact, the pass becomes a lesson in how small bodies shed skins and how those skins drift through space that other machines must cross. We have now built the internal logic of how a flare on a light curve can become a cloud with texture, and how that cloud can intersect a world without touching ground. In the next part, we translate those mechanics into specific Martian outcomes. We will follow a disturbance that does not hit the planet, yet still dims solar arrays, bends radio paths, and nudges a delicate atmosphere toward a louder electrical state. Picture Mars under a quiet sky, a pale sun, and a whisper-thin atmosphere that behaves more like a laboratory than a shield. Now place a broad envelope of ionized gas nearby, laced with fine dust and threaded by electric fields that change with sunlight. Nothing slams into the ground. Nothing leaves a crater. Even so, the space through which signals travel and the layer where charged particles gather can change character fast. This is the shape of a non-impact catastrophe. It is not a headline image. It is a sequence of small, measurable disruptions that stack, begin with the ionosphere. On Mars, this region builds and fades with solar radiation and with the flow of charged particles. Add an external source of ions and electrons from a vigorous coma and an active ion tail. The density profile can shift. Layers that refract radio waves can move upward or downward by tens of kilometers. That vertical migration changes how a signal bends, which changes where a deep space antenna on Earth expects to find a spacecraft. The effect is not always a full blackout. Often, it is an increase in phase noise that confuses the lock. Operators see a carrier that drifts and a rate that refuses to settle. The fix is patience, a change in geometry, or a switch to a frequency less affected by the current state of the plasma. Dust enters the picture through a different door. Mars already lifts dust with ease. When electric fields fluctuate, grains can charge. A charged grain interacts differently with the local environment than a neutral one. It adheres more readily to surfaces. It lofts more easily when winds or thermal contrasts push. In an electrically busy sky, small lifting events can merge. The planet does not need a global storm to feel the change. A regional haze that builds at an awkward time can drop solar array output on an orbiter during a critical pass. Power margins grow thin. Some instruments shut down to conserve energy. Telemetry arrives late. The ground imagines drama when the reality is 1% or 2% less sunlight at the wrong hour. Consider the spacecraft that rely on quiet fields. Star trackers use known patterns of light to orient a vehicle. Charged grains that streak across the field, or a subtle increase in background glow from excited atoms, can confuse those sensors. The onboard logic is conservative by design. When stars do not match catalog expectations, the computer pauses. It slews away from the glare, or it falls back to sun sensors. Orientation takes longer to confirm. A high-gain antenna points slightly off target. The link wobbles. In the control room, that wobble looks like a data rate that drops and then recovers. It is forgettable on a normal day. During a period of poor visibility from Earth, it becomes a rumor mill fuel. Radio silence does not need broken machines. It can come from normal machines protecting themselves. A spacecraft that senses unstable attitude or unexpected charging will enter a safe configuration. Non-essential systems sleep. The vehicle waits for ground commands. If the geometry puts Mars near the Sun in our sky, those commands may take longer to send with confidence. A gap that would be routine under clear viewing becomes an empty hour with no new frames on public sites. The usual cadence of images and updates slips. People ask what went wrong. The answer is often that nothing is wrong. The line of sight was bad, and the local plasma was loud, and the vehicle did exactly what it was designed to do. There is a subtle feedback loop worth naming. A temporary uptick in charged particles increases ionospheric variability. That variability causes more relay passes to miss their targets. Missed passes delay data that contain weather indicators. Without those indicators, prediction of dust activity is slightly worse. Surface assets then operate with wider margins. Wider margins reduce science time. None of this is a crisis. It is a slow erosion of efficiency. Over a week, the science team has fewer clean hours. Over a month, the accumulated delay becomes a real cost in missed opportunities. Energy balance offers another quiet lever. Dust that stays aloft changes how sunlight heats the surface. Dayside regions under haze warm differently than they would under a clear sky. Nightside cooling can also shift. These changes alter pressure gradients. Winds respond. The new winds pick up more dust along some fronts and less along others. A chain begins that is familiar to Mars climatologists. The seed was small, a change in the number of charged particles and in the ease with which grains could leave the ground. The outcome is not a planet on fire. It is a modest increase in storminess that arrives at an awkward season. It is responsible to balance these possibilities with counterpoints. The coma can pass and leave only the faintest trace in the electrodynamic environment. Spacecraft can ride through with no interruptions greater than routine. The ionosphere can remain within ranges that navigation teams handle every week. When we speak about radio silence, we must keep in mind that silence is often a scheduling artifact. A station hands off to another station. A pass ends because the Earth rotates. A conjunction window closes a link for hours. These are the rhythms of deep space operations. The constructive way to treat a non-impact threat is to define signatures ahead of time. Look for simultaneous shifts in electron density from one orbiter and changes in drag or accelerometer readings from another. Look for increased noise at the limb during spacecraft occultations. Look for correlation between regional dust indices and shortfalls in solar array output across vehicles that do not share the same latitude bands. If 2 or 3 of these signatures line up, the case for a real disturbance grows stronger. If they do not, the safer conclusion is that geometry and routine variability are sufficient to explain the blips. There is also a communication lesson for the public. Not every gap is a red flag, but some gaps are exactly when subtle physics do their work. When Mars sits near the Sun, press offices have fewer pictures that pass quality control. When spacecraft protect themselves, engineering teams go quiet to focus on recovery. It is better to set that expectation now. If a pause arrives, it fits a well-understood pattern. The story then becomes one of resilience and method. Machines built for hostile skies absorbed a noisy week, then reopened their eyes. A non-impact catastrophe is therefore a misnomer. It is rarely a catastrophe. It is a stress test that rarely makes good television. For a community that cares about planetary habitability and about reliable exploration, it still matters. The result is either proof that the system is robust or a list of tweaks that will harden the next mission. In the next part, we focus on why Mars offers so much leverage to small inputs. We will walk through the missing global magnet, the thin air, and the thresholds that dust and electricity cross with surprising ease. Begin with the missing layer that Earth takes for granted. Earth wraps itself in a global magnetic field that deflects much of the solar wind and shapes incoming charged particles into ordered belts. Mars does not. The planet keeps only scattered remnant magnetism locked in ancient crust. Those patches create local bubbles of protection, but they do not stitch together into a planetary shield. As a result, energy and plasma from space reach altitudes where the atmosphere is thin and easily perturbed. What would be background hiss near Earth becomes a voice that can be heard by instruments and sometimes by mission controllers who are watching for stable signals. The second baseline is the air itself. Mars breathes a very thin mix, mostly carbon dioxide, with surface pressure that is less than 1% of Earth's sea level. Thin air means two things at once. It provides little braking for incoming particles and fragments, and it makes the atmosphere easy to move with small inputs. A gentle pressure gradient that would barely stir fog on Earth can loft dust on Mars. A small change in upper atmospheric chemistry can alter how radio waves bend. When we talk about leverage, this is what we mean. The system sits near thresholds that are easy to cross. Consider the ionosphere. On Mars, it is shaped by sunlight and by charged particle input from the sun and from any nearby plasma environment. There are layers where electrons and ions are abundant, and these layers rise and fall with time of day, season, and space weather. The refractive properties of those layers determine how signals curve and how quickly a radio locks onto a spacecraft. A small change in electron density can move a layer by tens of kilometers, which changes the path length for a signal. In practice, navigation teams see this as extra noise in the phase and rate. Most days, the noise is manageable. On a few days, during a geometry that is already poor, the same noise causes a link to wobble or a pass to be missed. Dust is the amplifier that converts small atmospheric nudges into visible weather. Grains are fine, often smaller than a human hair, and they carry charge readily when they rub or when they sit inside variable electric fields. Charged grains lift more easily and stick to surfaces more tenaciously. Mars has a feedback between dust and sunlight. Dust absorbs sunlight, which warms the air, which increases lifting, which lofts more dust. The loop can remain regional, or it can connect across basins and channels to join a broader circulation. Global storms are not the norm, but the seeds for larger events are sown by differences as small as a few percent in heating or pressure. This is why a modest external push can matter. It need not start a planet-wide storm to change the schedule of a relay or the power budget of a rover. Thermal inertia adds another lever. Many Martian surfaces warm quickly by day and cool quickly by night. That daily swing drives upslope and downslope winds that are reliable but sensitive. Change the timing of heating by dimming the sun with a faint haze, and those local winds arrive late or early, stronger or weaker. The altered winds push dust where it was not expected to go. They also change how near. Surface layers exchange heat and momentum with the air above. Mission planners model these cycles in order to choose landing seasons and orbit geometries. The models are good, but they do not anticipate every perturbation. Add even a small external plasma disturbance, and the timing can slip just enough to force conservative choices on operators. Topography is the quiet accomplice. Mars is a world of basins, escarpments, and vast volcanoes. Air flows through Valles Marineris like water through a channel, and over Tharsis like air over a mountain range. These structures focus and deflect winds, which in turn focus and deflect dust. A small change in the upstream environment can be magnified when it reaches a canyon mouth. The result is a local surge that would never appear in a global average. Spacecraft do not live in global averages. They live in passes with finite durations and power budgets that were written with margins based on typical days. Atypical days collect interest quickly. Another vulnerability lies in electrostatics. On a dry world with fine grains, surfaces can charge relative to their surroundings. Spacecraft manage this with materials and grounding schemes. Still, unusual environments can add electrons or remove them faster than expected. The outcome is often benign. A sensor saturates temporarily, A reset is required, a margin is consumed. In a small number of cases, a static discharge can flip a bit or trip a protection circuit. Engineers plan for this regime with error detection and with conservative thresholds. The point is not that the machines are fragile. The point is that Mars provides more opportunities for these edge cases to occur because the natural noise floor is low and the shielding is minimal. We should balance this picture with the resilience built into modern missions. Orbiters carry multiple attitude sensors and can switch to coarse sun tracking when star fields look messy. Communication networks have overlapping coverage that can pick up a missed pass. Spacecraft power systems are designed to ride through dust loss for a while, and the newest surface missions often carry radioisotope heat and power to de-risk cloudy seasons. These measures do not remove sensitivity, they manage it. They also require time and bandwidth to operate, which is exactly what an observation gap makes scarce. Known versus unknown remains our axis. We know Mars is a responsive environment, with weak shielding and low inertia in many atmospheric processes. We do not know which small inputs will align during this particular pass. We know that small inputs can be hard to diagnose when telescopes point near the Sun and when relay windows are short. We do not know whether the visitor will shed material in a way that matters. The responsible posture is alert but calm. Measure what can be measured, note what cannot, and resist the urge to fill blanks with drama. At the 5-part mark, we restate the through line. The closest approach is distant by common sense, yet Mars turns small disturbances into operational realities. If anything goes wrong, it will most likely be a cluster of subtle effects, not a single cinematic blow. In the next part, we move from the planet to the machines. We will walk through the specific ways spacecraft sense the world, the failure modes they prefer, and the graceful ways they pause when the sky grows noisy. Begin with how a spacecraft knows where it is and where it points. Orientation lives inside star trackers, tiny telescopes that take pictures of the sky and compare the pattern of points to a catalogue. When the pattern matches, the computer knows which way the spacecraft is facing to a fraction of a degree. The system is elegant, but it has assumptions baked in. The stars are steady, the background is dark, and stray streaks from charged particles or micrometeoroids are rare. Disturb any of those assumptions and the solution can wobble. The computer does not panic. It becomes careful. It slows down and asks for a second opinion from gyroscopes or sun sensors. During that pause, the high-gain antenna can drift slightly off target. The data rate falls. On the ground, graphs flatten, and a pass that would have been routine dribbles to an early end. Safe mode is the next line of defense. It is not a failure, it is a posture. When sensors disagree or when power drops below a margin, the spacecraft pivots to a survival attitude and sheds non-essential work. Instruments that draw a lot of power turn off. The antenna may switch to a wider beam with lower data rate. The flight computer may reduce activity and wait for ground commands. The idea is simple. Protect the bus, keep the batteries healthy, stay thermally safe, and keep the sun in view. A safe mode can last minutes, hours, or days, depending on what triggered it and how quickly the team can diagnose the cause. In a noisy sky near conjunction, even sending the first reset command can take longer than normal. That delay is not a sign of doom. It is a consequence of geometry and caution. Consider the communication chain. A spacecraft speaks through a sequence of antennas and frequencies. It has a low-gain voice that is easy to hear, but carries little information. It has a high-gain voice that carries images and spectra, but must point precisely. Deep space antennas on Earth listen and hand off as the planet turns. Solar proximity adds hiss to the line. A patchy ionosphere near Mars can bend the path and add phase noise. Each element can eat a little margin. Add them together, and a pass that was expected to deliver a full buffer of data may deliver only a fraction. The rest must wait for the next orbit. When several orbits in a row land in awkward geometry, schedules slip. Teams who understand these rhythms shrug and adjust. Audiences who expect a steady scroll of pictures begin to worry. Power is a quiet constraint that shapes every decision. Orbiters rely on solar arrays unless they were built with radioisotope power. Dust on panels lowers current. Off-pointing to avoid glare lowers current. Instruments that draw steady wattage become luxury items when margins shrink. Engineers triage. They keep thermal control and core avionics healthy. They defer imaging campaigns. They might pause high-voltage instruments that are more sensitive to electrical noise. From the outside, the mission looks sleepy. Inside, it is awake and conservative. Sensors face their own forms of confusion in a disturbed environment. Charged particles can spur flashes in detectors that mimic stars or cosmic rays. Cameras can pick up streaks that the star tracker logic interprets as false points. Magnetometers can see fluctuations that are physical but not harmful, which still trigger flags in monitoring scripts. Accelerometers can register tiny drag changes at low periapsis altitudes, which are interesting science but uncomfortable for navigators, who must maintain tight control of the orbit. The correct response to such complexity is to slow down. You gather more data, you run longer filters, and you back away from the most aggressive modes until the picture clears. Redundancy exists for these moments. A typical orbiter carries multiple independent ways to know attitude. If the star tracker is unhappy, the spacecraft can use gyros to coast through the gap, then reacquire stars when the field is cleaner. If the high-gain link is unstable, the vehicle can switch to a medium-gain link for a while and raise the data rate later. If one power regulator runs hot, loads move to another path. These cross-checks cannot prevent every interruption, but they break chains of failure and keep small glitches from growing teeth. Recovery follows a choreography that is familiar to flight teams. First, you stabilize attitude. Then you confirm power state and battery charge. Next, you check thermal margins. Only then do you begin to bring back instruments one by one. You test each instrument with short exposures or low voltages. You watch the bus for reactions. You raise data rates gradually, and you verify the ground link at each step. This measured approach protects the spacecraft from flapping between states. It also lengthens the period of low public output. A day of careful recovery looks like silence to those who only see the headline image feed. Sometimes, an outage has nothing to do with the environment. Ground stations can have maintenance windows. Weather can affect a dish. A software patch can be staged and the vehicle can be placed in a quiet mode while it installs. During conjunction, these routine events arrive in the same week as the natural gaps. The pile-up feels ominous. The antidote is transparency about operations and reminders of the normal cadence of deep space life. Even the most robust mission spends many hours every week doing housekeeping that never makes a highlight reel. There is a human factor that matters here. Teams train for off-nominal periods. They run simulations with noisy skies and ambiguous telemetry. They practice recovery from safe mode with missing data and with conflicting sensor readings. These rehearsals do not guarantee a smooth week, but they turn surprise into memory. When a real pass goes sideways, the team recognizes the pattern. They slow the tempo and work the plan. The public sees a quiet feed. The room hears normal voices taking normal steps. We keep our through line in sight. The most plausible stress on Mars missions during this encounter is a cluster of small effects that nudge sensors and links into conservative behavior. Star trackers will occasionally be confused. Power will sometimes run tight. Safe modes will be entered by design, not by panic. Communication will wobble and then return. In the next part, we step back out to the wider environment. We will examine how a brief episode of activity can seed a long tail of debris, and why that tail matters even when the headline event passes without spectacle. A close pass that feels quiet in the moment can plant a problem that outlives the headlines. Debris remembers, not as a single cloud that stays compact, but as families of particles sorted by size, age, and the forces that guide them. A short burst of activity near closest approach is like opening a window during a windy evening. The gust is brief. What enters keeps drifting through the house for hours. In space, the house is the volume Mars will revisit again and again. The furniture is every orbit a spacecraft must fly with precision. Think first about the smallest travelers. Submicron dust behaves more like smoke than gravel. It couples strongly to sunlight and to electric fields, which shepherd it into broad, diffuse structures that stretch far from the parent. These grains rarely strike hardware directly. Their influence is indirect and cumulative. They glow faintly and raise backgrounds for sensitive detectors. They alter the local plasma environment by picking up charge. They add a soft veil that only instruments notice. The signature is a small rise in instrumental noise that persists longer than the outburst that created it. Mission teams log it and adapt, then move on. The point is not drama, the point is endurance. Millimeter to centimeter grains live in the middle ground. Light pressure still matters to them, but inertia begins to assert itself. These grains preserve more of the velocity they had at release. They gather into streams that follow the parent orbit with measurable lag. If a burst of shedding occurs near the time of closest approach, a ribbon of these grains can form with a phase that sits just ahead of or behind the parent track. Planetary gravity can comb these ribbons into structures that repeat. The result is a meteoroid stream in the making. It does not need to be dense to be important. A single fast-moving pebble that finds a panel or a radiator has no sense of scale. It only has kinetic energy. Larger fragments, the kind that you could hold in 2 hands, are least likely to populate the space near Mars on this pass. Geometry and timing work against them. If they exist at all, they drift on paths that are more easily tracked and avoided. The more insidious hazard is the vast population of grains too small to see, yet large enough to sting. Their dynamics are messy. A weak outgassing jet can change their spin and apply a tiny thrust. An encounter with an ionized region can alter their charge and their path. Over weeks and months, these microforces stretch a compact production event into a long, thin hazard that crosses key orbital planes at repeatable times of year. Mars' orbit is not a single ring where everything travels at the same height and speed. It is a stack of corridors used for science, for relay, and for aerobraking. Each corridor favors certain altitudes and inclinations, because those choices minimize fuel and maximize contact windows with Earth. A persistent stream that intersects any one of these corridors becomes a scheduling tax. Teams add extra attitude changes to protect optics during crossings. They alter pointing plans to keep radiators out of the wind. They create do not dwell zones where star trackers are most likely to be confused by streaks. None of this guarantees a strike. It guarantees that careful operations become more careful still. Beyond Mars, debris becomes a population that the inner solar system must catalogue. The smallest grains spiral outward or inward as light pressure and thermal forces nudge them. Some fragments find orbital resonances that repeat encounters with planetary longitudes. The probabilities are low for any single piece to become a problem. The measure that matters is not the fate of one grain. It is the flux that a spacecraft will experience over a mission lifetime. A small increase in flux shifts the odds for a critical hit by a small amount. If you manage dozens of vehicles over decades, that small amount becomes a planning variable. Shielding and Whipple bumpers do not make the risk vanish. They buy time and reduce the number of fragments that can penetrate, but they add mass and cost that must be justified. Debris fields also complicate interpretation. A detector that reports more micro-impacts can mean the environment is richer, or it can mean the vehicle flew through an old stream at a seasonal crossing. Sorting the two requires years of counts and careful correlation with geometry. The work is patient and unglamorous. When the pattern emerges, the lesson is simple. The sky has rhythms that missions must dance with. A single visitor can add a new rhythm that was not there before. There is a comforting counterpoint. Most cometary streams disperse. Solar radiation pressure and planetary encounters spread particles along orbits until the flux drops back toward background. The clock for that dispersal varies with size and with the initial conditions of release. A stream seeded at a relatively large distance from Mars, with modest production and no strong gravitational focusing, can fade on timescales that are short compared to a decade. If the object does not continue to shed near the same geometry on later passes, the corridor heals itself through natural diffusion. This is why the worst case for persistence requires repetition. One burst is a reminder to be careful this season. A series of bursts seeds an environment that becomes part of the long-term forecast. Mission designers already live in this world. They check meteor stream calendars for Earth crossings. They plan critical deployments away from known showers. A similar playbook applies at Mars once a new stream is suspected. Shift aerobraking campaigns by a few weeks. Align high-value observations with phases of lowest risk. Store attitude quaternions that minimize exposed areas during brief crossings. The cost of these mitigations is real, but small compared to the cost of replacing a mission that was unlucky on the wrong day. It remains uncertain whether this visitor will seed such a stream in a way that Mars will notice. The distance at closest approach and the short duration of geometry argue for modest production near the most sensitive corridor planes. A minority view holds that interstellar material might include more fragile components that crumble into excess dust, which would raise the odds for a detectable stream. Evidence is limited for that view. The practical approach is to watch the sky with particle counters and cameras, to compare notes across platforms, and to update hazard maps if a new rhythm appears. The debris problem is not a cinematic threat. It is a paperwork threat. It adds checklists. It adds caveats to operations plans. It adds an asterisk to the phrase, routine pass. The payoff for taking it seriously is measured in missions that keep flying without drama. In the next part, we follow the chemistry that might ride with the dust. We will see how a vigorous carbon dioxide coma meets a thin Martian sky, and how even a small dose of exotic volatiles can sketch faint lines in an atmosphere that records everything. Imagine an atmosphere that keeps a careful ledger. Mars carries so little air that every gram of gas and dust deposited or stirred can be traced in its books. Now, placed near that sky, a visitor wrapped in a carbon dioxide-rich coma with hints of other volatiles. The stage is set for a meeting of inventories. It is not an exchange in the way a thick terrestrial atmosphere would experience. It is a light brush of molecules and ions across a system that responds strongly to small nudges. Begin with what is safe to say. The coma of a strongly active comet is a mix dominated by carbon dioxide and water when far from the sun, with carbon monoxide and trace organics adding character to the spectrum. In the rare case of an unusually early active interstellar visitor, the balance can tilt toward carbon dioxide at larger distances. That balance matters because carbon, the dioxide, is already the primary component of the Martian air. Add a little more, and you do not change the identity of the gas. You change where and how the gas participates in radiative and chemical processes. A brief pulse of external carbon dioxide near the top of the atmosphere will not thicken the air in any lasting way. It can still alter the temperature of layers for hours or days by changing how sunlight and infrared radiation are absorbed and emitted. Ion chemistry is the first frontier in this encounter. The coma and ion tail carry charged particles that can enter the ionosphere and participate in reactions that move electrons around. When additional carbon dioxide ions and water group ions arrive, they change the rates of familiar reactions. Recombination rates shift. The altitude of peak electron density can rise or fall. Radio occultation experiments will see this as a warping of the profile during a passing window. A moderate change in the shape of that profile can bend signals differently. Mission teams will call this a propagation effect, which is accurate. It is also a chemistry effect, since the propagation medium is set by the mix of ions and neutrals that are present. Below the ionosphere, neutral chemistry receives whatever survives descent. Most of the coma material will not reach deep layers in any concentrated way. The pieces that do arrive will be thinly spread across a broad region. Even a thin delivery can matter for tracers. If a plume carries small amounts of reactive gases, such as carbon monoxide, or contains simple organics that can be photolyzed, those molecules join cycles that set the faint signature gases that orbiters measure for years. It remains uncertain whether any delivered package would rise above the noise of native surface sources and seasonal exchange. Evidence is limited, but one inference is that the best chance to see a trace would be immediately after the encounter and at high altitude. Spectrometers that watch the board limit ultraviolet and infrared wavelengths would be the instruments most likely to notice a small excess. Dust acts as both courier and catalyst. Grains that have ridden in the coma carry adsorbed gases and organics on their surfaces. When those grains mix into a Martian haze, they add surfaces where reactions can proceed more easily. Heterogeneous chemistry on dust is already a topic on Mars, since native dust affects the balance of odd oxygen species and the fate of trace gases. The arrival of grains with unusual coatings could change rates locally for a short time. One possibility is a slight alteration in the lifetime of methane where present, since radicals produced on sunlit dust can influence oxidation pathways. A competing view suggests that the effect would be buried under the noise of daily and seasonal variability. Both views can be tested with careful time series if instruments remain stable across the critical period. Thermal effects are simple to name and subtle to measure. Extra carbon dioxide at high altitude increases infrared cooling in some bands while changing ultraviolet absorption higher up. The net result can be a shift of a few Kelvin in specific layers over short periods. A small shift still changes density where orbiters skim during aerobraking like passes. Navigation teams may observe tiny differences in drag that are consistent with a slightly altered thermal structure. The same changes can move the sound speed and the scale height in ways that are invisible to the eye, but that matter to engineers who model upper atmospheric flight. There is a question that attracts attention whenever external material approaches a world we want to explore. Could complex organics delivered to the surface complicate future life detection tests? The conservative answer is that any global signal is unlikely from a single pass at this distance. Concentrations would be tiny and quickly diluted by mixing and by photochemistry. A localized dust fallout could leave a patch with an unusual signature. It would still be difficult to distinguish from signals created by Martian geology and known processes without careful isotopic and structural analysis. It remains uncertain whether the visitor carries organics that differ in obvious ways from what Mars already hosts. If any difference exists, isotope ratios would be the most informative, and those require sample return or very sensitive in situ techniques. There is also a climate narrative that deserves restraint. A brief encounter with carbon dioxide-rich gases near the top of the atmosphere is not a terraforming event. Mars will not warm permanently. The radiative budget of the planet is governed by the mass of the atmosphere and the balance of dust and clouds over seasons and years. What the encounter can do is write a short chapter in that longer book. A mild change in haze, a tweak in upper-level temperatures, a few days of altered ionospheric structure. These are passing footnotes that nevertheless offer scientists a probe of how the system responds to small, timed perturbations. The responsible way to watch this crossroads is to set up paired measurements. LIMS scans of trace gases and electron density profiles before and after the encounter, thermal sounding of upper layers across local times, correlation with dust opacity indices derived from imaging. Look for coherence in time and altitude between these streams. If a signal appears in only one and not the others, treat it as an instrument quirk. If several move together in the right sequence, the case grows that the visitor left a chemical fingerprint, however faint. Known versus unknown guides the tone. We know the comae composition family and the basic reaction networks in a carbon dioxide atmosphere. We do not know the exact inventory of trace species in this specific visitor. We know Mars will respond measurably to small injections in the upper atmosphere. We do not know whether that response will rise above seasonal patterns in ways that are easy to isolate. In the next part, we apply that caution to an even more delicate topic. We will examine contamination claims through a planetary protection lens, and we will separate the credible risks of confusing signals from the more dramatic but less supported stories about life carried between stars. The word contamination carries weight that can tilt a conversation before facts enter the room. It suggests invasion and irreversible change. Planetary protection uses the word differently. It treats contamination as any addition that confuses interpretation or alters an environment in ways that complicate science or future exploration. Under that definition, a few molecules in the wrong place at the wrong time can matter as much as a large delivery that makes headlines. The challenge is to sort two very different questions. Could the visitor deliver material that interferes with measurements on Mars? Could it deliver biology? The first is plausible in narrow ways. The second requires care and restraint. Begin with the conservative case. Instruments that search for life, or for the chemical fingerprints of past habitability, often rely on detecting faint patterns in a sea of background signals. Methane has been a focus because it is chemically fragile in a carbon dioxide atmosphere and because some processes that produce it can be biological. If a visitor introduces trace organics or gases along a track that later passes over a sensitive instrument, the reading might pick up a small bump that is not of Martian origin. This is a false positive. It does not mean a laboratory on Mars detected life. It means the instrument detected a molecule that can be produced by life, by geology, or by exotic chemistry riding a dust grain. The fix is not to fear the air. The fix is to run controls, to take repeated measurements across time and locations, and to look for isotopic signatures that point to a process rather than a source. Complex organics deserve a different paragraph. These are molecules with carbon backbones that can be assembled in space by non-biological processes over long times. Some comets carry a rich inventory of such compounds. An interstellar visitor could carry a different mix, shaped by formation conditions far from our Sunday. It remains uncertain whether any such material can arrive intact at the Martian surface after a distant pass. Evidence is limited that dust from a coma at such distance can seed ground-level patches with enough richness to confuse carefully designed experiments. One possibility is that a localized haze fallout could add exotic coatings to soil grains. Another possibility is that any delivered organics would photolyze quickly, leaving behind fragments that are less informative. Both possibilities can be managed by field protocols that avoid freshly coated surfaces when collecting samples. The more dramatic claim is that viable biology could travel this way. A minority view holds that some microbial forms might survive interstellar cold within protective matrices and then wake in a new environment. The mainstream view is cautious. Survival across interstellar time, inside an object that vents and warms at unexpected distances, would be a chain of luck that stretches credulity. Radiation, thermal cycling, and chemical reactions would conspire against fragile structures that life uses on Earth. There is no law of nature that forbids all survival, yet there is also no evidence that supports it for this case. Responsible storytelling keeps this category in speculation and builds walls between it and operational planning. Planetary protection agencies approach these problems with procedure rather than drama. They classify missions by the risk of forward contamination and back contamination. They specify cleanroom standards, sterilization steps, and documentation. For Mars, the watchwords are, "Do not confuse the record," and "Do not leave irreversible fingerprints." An external dust event is outside human control, yet the same logic applies. If the sky changed that week, then annotate the notebook. If a detector saw a signal that looks new, then ask whether the viewing geometry and the known plasma environment can explain it. The goal is not to prove absence. The goal is to keep a chain of custody for interpretation that is honest about context. False positives are a recurring issue even without visitors from afar. Instruments are sensitive to background conditions and to their own health. A warm detector produces different noise than a cold one. A solar flare can seed a dataset with spikes. A dust storm can change the local chemistry in ways that mimic other processes. Teams already navigate these waters by using comparison and redundancy. A possible methane signature is weighed against wind patterns and against parallel measurements of other species that should ride with methane if a specific process is responsible. If those companions are absent, the single line loses weight. This conservative posture protects against both overclaiming and underclaiming. Communication with the public is another part of planetary protection because it shapes expectations. When a press release mentions organics, many people hear life. When it mentions contamination, many hear permanent damage. The better phrasing speaks of detection limits, of control sites, and of the difference between presence and provenance. An instrument can find a molecule without knowing where it was made. The follow-up study aims at that second question. During a period when a visitor has brushed the sky, patience in messaging is not just wise. It is necessary. It preserves trust that results are not rushed to fit a headline. Could any contaminant dial be turned far enough to affect human missions? For this pass, the answer is almost certainly no. The quantities involved are small, and the residence times of reactive species in the upper atmosphere are short. The more sensible concern is bookkeeping. If a future rover reads a faint and surprising pattern in a location known to have been downwind of this encounter, teams will want archived context. That is why the most useful action now is to collect background measurements before and after, to maintain stable calibration, and to mark the calendar with geometry that later researchers can reference. The through line returns. Planetary protection is about clarity of interpretation and respect for environments we hope to study and visit. A distant pass by an active visitor can add noise to that clarity. It can add trace molecules and unusual dust surfaces that nudge sensitive readings. It remains unlikely to deliver biology or to alter a planet in any lasting sense. The correct response is discipline. Measure, annotate, repeat. In the next part, we leave chemistry and return to mechanics. We will look at the small moons that circle Mars, why they are already stressed by tides, and how even tiny nudges can alter their long futures. Begin with the smaller worlds that keep close company with Mars. Phobos and Deimos look like captured rubble, irregular and dark, with histories written in grooves and boulder fields rather than smooth maria. They already live precariously. Phobos circles so low that it rises and sets multiple times in a Martian day. Tides from Mars tug at it, and over long stretches of time the orbit decays. Deimos sits farther out, slow and quiet, but it also carries the look of a body that was built from fragments and dust. Neither moon has a deep gravity well or strong internal cohesion. They are aggregates that hold together through a mixture of gravity, friction, and the gentle cement of fines filling voids. Tides are the first pressure to consider. Phobos moves inside the synchronous radius, so Mars pulls it gradually inward. The pull is not violent in a single year. Over geologic time, it is destiny. Strains show up as parallel grooves that some interpret as stress markers. Other studies argue that many grooves are chains of secondary craters from past impacts. Either way, the surface tells a story of repeated shaking and settling. The blocks rest at angles that would be unstable in stronger gravity. The fines sift and resettle when vibrations pass through. Deimos feels smaller tidal forces because it orbits higher, yet its low density hints at porosity that could respond to gentle nudges in ways that are not intuitive. In both cases, small external inputs can rearrange local slopes and can move the clock hands on long-term evolution by tiny ticks. How might a visitor that never comes close, by daily life standards, matter to such moons? The answer is indirect and conditional. Direct gravitational influence at tens of millions of kilometers is negligible for the bulk motion of either moon. The important routes are through debris and the electromagnetic environment. If a burst of small grains arrives in the Martian system, even a thin flux can pepper Phobos because it sweeps a volume quickly and presents a large face relative to its mass. Each micro-impact is inconsequential. A field of micro-impacts can loosen regolith, can shake larger blocks a millimeter downslope, and can feed a slow migration toward lower potential surfaces. Over months, the effect hides inside noise. Over a season of elevated flux, the effect can register in the statistics of fresh boulder trails, or in the appearance of new albedo patches, where bright material has been exposed. Electrostatics offers a second lever. Phobos and Deimos spend part of every orbit moving in and out of plasma regions that include the Martian wake and the solar wind. Charging is a known phenomenon for airless bodies. When the external environment grows more variable, surfaces can build larger potentials across short distances. Fines can lift and hop. The famous dusty horizon glow seen around other airless worlds speaks to such motions. If the encounter adds variability, the hopping becomes more common for a while. This does not dismantle a moon. It does alter the rate at which dust migrates from highs to lows. Over time, migration changes local slopes and the ease with which later impacts will trigger small landslides. There is also the issue of how small moons respond to passing particle streams that alter the space around them. A slight increase in charged particles can create currents that flow along the surface or through plasma sheaths. Instruments on orbiters have seen such currents near other bodies. On Phobos or Deimos, currents could add a new source of noise for magnetometers on passing spacecraft, or for radios that bounce signals off the moons during experiments. These are minor nuisances for engineers. They are also signatures that something external is changing the local environment. When multiple teams report similar nuisances around the same times, the case strengthens that the moons are feeling the tail of an event that never touched ground. A natural question follows. Could a short episode of elevated micro-impacts trigger something more dramatic, like a surface slump on Phobos that exposes fresh material over a broad area? One possibility is that a slope already near failure could be tipped by a sequence of small taps. A competing view suggests that local seismicity from ordinary meteoroid hits dominates such events, and that any additional flux from a distant visitor would be lost in the baseline. It remains uncertain which regime applies during this pass. The safe prediction is that if anything changes visibly, it will be small, like a fresh streak on a wall of regolith or a new boulder trail cutting across dust. Orbit change is the spectre that often appears in conversations about fragile moons. Here the numbers give comfort. At the stated separation, and with the expected mass of the visitor, there is no mechanism for a sudden shift in the paths of Phobos or Deimos. Their long-term fates remain, set by tides and by the occasional direct impact by local meteoroids. The encounter we study can add dust and can add electrical noise. It cannot reach out and twist a trajectory that has been measured for decades. This distinction helps separate cinematic anxiety from the slower reality that mission planners address. Yet even in this quieter framing, the moons matter because they are bellwethers. They respond quickly to changes in the particulate and plasma environment. They are also practical hazards when they shed material. Phobos has been linked in models to transient dust rings around Mars, dusty shells that are faint and short-lived. If a new source of fine grains appears in the system, those shells could be refreshed or slightly thickened for a time. Spacecraft that cross the orbital plane of Phobos would see the effect first as a modest rise in micro-impact counts, or as a need to mask star tracker fields during particular longitudes. Careful correlation with the location of the moons would help confirm such a link. Operations around the moons would adapt with familiar tools. Avoid long stares through the most contaminated longitudes. Store attitude profiles that reduce the exposed area of sensitive surfaces. Use orbit geometries that cross suspect planes at higher speeds or when shadows reduce scattered light. None of this would be new, only newly relevant if the environment changes for a few weeks. The reward for such caution would be simple. Missions keep flying, instruments keep collecting, and later analysis can turn a handful of odd signatures into a chapter about how small bodies serve as canaries for space weather inside a planetary system. We keep the through line in view. The moons of Mars are already under stress from tides and from their own fragile structures. A distant visitor cannot wrench them from their paths, but it can, through dust and plasma, raise the background in which they live. If any visible outcome arrives, it will likely be subtle, a mark on a slope or a thin veil in a plane, not a wholesale change in destiny. In the next part, we take that thin veil idea to its logical end. We ask what a temporary ring around Mars would look like, how it would complicate traffic, and how quickly it might fade once the sky calms. Picture a thin sheet of dust and pebbles wrapped around Mars like a ghostly belt. It does not glow like Saturn's rings. It is faint and patchy, a veil that cameras might only detect with careful backlighting. Such a structure can arise from several sources. Micrometeoroid impacts on Phobos, slow landslides that loft grains off weak slopes, or a brief enrichment of small particles seeded by a passing visitor. Most of the time, the shell is too thin to matter. Increase the population even a little, and it becomes a logistical problem. The issue is not beauty or spectacle. The issue is traffic. Mars operations depend on predictable corridors. Orbiters use near-polar paths for mapping, near-equatorial paths for relay, and elliptical paths that skim the upper air for aerobraking campaigns. Each path crosses the orbital planes of the moons. Each path passes through longitudes where dust is more likely to gather. A temporary ring would add intersections where none were planned. The hazard lives in relative velocity. A grain that weighs less than a paperclip carries surprising energy when it meets a spacecraft at kilometers per second. The spacecraft does not care that the ring is thin. It cares about the impact point on a radiator fin, a star tracker lens, or a solar array hinge. Traffic engineering in space is a game of probabilities and geometry. Teams predict where densities will be highest using simple models. Dust that leaves Phobos tends to drift near its orbital plane. That plane is tilted a little relative to the Martian equator. Streams created by a distant visitor would align with the path of the parent and with whatever small forces shaped the release. These patterns create bands of slightly higher risk. If a temporary ring forms, those bands become do not linger zones. Orbit solutions are adjusted to cross them quickly, and at angles that reduce exposure of sensitive surfaces. Instruments are powered down for a few minutes during crossings to protect detectors. These are small changes that add up to smoother survival. Kessler conditions are the nightmare that haunts traffic planners. The term describes a runaway cascade where collisions create fragments that create more collisions. Around Earth, this cascade is driven by large and fast-moving human-made objects. Around Mars, the landscape is different. The number of large satellites is smaller, and the relative speeds and densities are lower. A natural ring made of dust does not behave like a swarm of dead spacecraft. It cannot generate a self-sustaining cascade that fills all of space with shrapnel. That is the good news. The caution is that even without a cascade, the addition of a thin ring increases the cumulative chance of small impacts across many orbits and many months. A mission that would have flown clean for years might pick up a handful of tiny scars. One unlucky strike on a vulnerable part can still end a career. Detection is part of mitigation. Instruments that count micro-impacts provide the earliest warning. If the rate increases above background during specific longitudes, planners mark those sectors. Star trackers offer a second clue. An increase in streaks along one edge of the field hints at a directional flow of grains. Radio occultations offer a third clue when signals skim the limb. A slight increase in scintillation can betray extra particles along the path. None of these signatures requires dedicated campaigns. They arrive as side effects of routine operations. The trick is to correlate them and to share the patterns across missions. A single report can be noise. A handful aligned in time and location becomes a map. There is comfort in the physics of mission. Decay. Small grains do not remain in tidy rings forever. Light pushes them, the solar wind charges them, and electric fields accelerate them. Mars itself breathes on them with tenuous drag at the top of the atmosphere. Orbits precess and alignments shift. What forms as a thin belt tends to smear into a thicker, fainter structure that drops back toward background levels. The timescale for this clearing depends on grain size, charge, and launch conditions. Many scenarios fade over seasons rather than decades. If the passing visitor does not return to seed the same corridors again, the veil thins naturally. Operations culture already contains tools for this moment. Mission designers accept that space is never perfectly clean. They add Whipple shields in front of high-value tanks and avionics. They place radiators and star trackers where exposure is lower during most attitudes. They write procedures that rotate arrays during suspected showers. These choices cost mass and complexity. They also prevent a small pellet from ruining a decade of work. If a temporary ring forms, teams enact these measures more often, then relax as counts fall. A broader question lingers. Would a ring around Mars change the long-term viability of staging operations there? The responsible answer is no for the scenarios that flow from a single distant pass. The ring would be too faint and too transient to rewrite the playbook. It would complicate a season, not a century. Sustained risk would require repeated seeding events or a structural change in the sources from the moons. That is a different problem, and it belongs to studies of moon evolution and impact rates, not to a one-time visitor. Public communication around rings often leans toward headlines. The word conjures images of wide, bright bands and dramatic arcs. The truth at Mars would be more like a dusty hallway in late afternoon light, visible only when the sun catches it just right. For engineers, it would be a spreadsheet of adjusted attitudes and a few extra hours of analysis. For scientists, it would be an opportunity to learn how dust moves through the Martian system and how the moons feed and erase delicate structures. For audiences, it should be a reminder that space is a story of small things in large numbers, creating patterns that matter. We keep the through line clear. If a ring appears, it would be a product of increased small particle populations, not a chain reaction of machinery smashing into machinery. It would fade as forces smear it out and as particles fall into new paths. It would require attention for a while, and then it would become a footnote. In the next part, we examine a different kind of persistence. We look outward toward Earth and ask how small changes in many orbits can add up to ripples that arrive years later. That chain reaction is not a spectacle either. It is the slow arithmetic of resonances and gentle thermal drifts. Stand far back from the immediate scene and watch time slow to the pace of orbits. The encounter near Mars ends, the visitor continues on, and the sky seems to recover. Yet dynamics keep accounts open. Tiny changes in paths can grow into meetings years later, not through intention, but through the quiet mathematics of resonance and drift. This is the chain reaction that matters for Earth. It does not arrive like a shout. It arrives like a whisper that repeats until you finally notice the pattern. Begin with resonances. An orbital resonance is a timing agreement between two paths. If a small fragment circles the Sun and returns to a particular longitude every few years while Earth reaches a matching longitude at a related rhythm, the two can see each other again and again. The fragment does not need to cross Earth's orbit at the start. It only needs to carry a period that plants it near a gate at repeat intervals. Planetary gravity provides gentle tugs each time the meeting is close. Over dozens of revolutions, those tugs add up. The fragments, path shifts. Gates that were closed open a crack. A crack is all that a long timeline requires. Now add thermal drift, a slow propulsion delivered by sunlight itself. Small bodies warm on their day side and re-radiate heat on their night side. The imbalance in that radiation creates a minuscule thrust. Over many years, the thrust moves the semi-major axis by small amounts. For meter-sized pieces, the shift can be kilometers per year. For smaller fragments, it can be faster or slower depending on spin, shape, and material. This is not fiction. Engineers account for it when predicting the future positions of near-Earth asteroids. For a population of fragments created during a busy pass, thermal drift acts like a patient shepherd. It nudges some pieces toward resonant lanes that were unreachable before. Once in a lane, gravitational tides do the rest. Consider how these effects might recruit a family of fragments into a future encounter field. One possibility is that the visitor, after its brush with Mars, sheds small pieces that take on a spread of orbital periods. Most will disperse harmlessly. A minority will wander near weak resonances with Mars or Earth. Each pass through a resonant zone delivers a tiny push. Over a decade, these pushes can rephase the objects. A competing view suggests that the hyperbolic nature of an interstellar visitor leaves most fragments on escape trajectories that dilute quickly, with only a thin tail captured into bound orbits. It remains uncertain where on that spectrum this event sits. Evidence is limited in real time. The inference can only be tested by patient surveys that count faint streaks and by dynamical models that are improved once the post-encounter orbit of the parent is pinned down. If a small flux does materialize near Earth years later, it will not look like a hailstorm. It will look like a new trickle superimposed on the perennial drizzle of meteoroids we already live with. Most of the particles would be millimeter scale, or smaller, which burn up harmlessly in the upper air. The difference lives in rare events. A decimeter fragment that arrives at the wrong speed and angle can produce an airburst that rattles windows and draws headlines. The odds for any given year remain low. Over decades, added flux moves those odds by fractions. Space agencies who plan for deep time care about fractions. They shape observation programs and insurance policies, even when the sky looks calm. Near-Earth space would record the change first. Radar and optical surveys log meteoroid counts. Satellite operators track small anomalies that accumulate on exposed surfaces. Meteor cameras tie fireballs to radiant points in the sky. If a new stream exists, these systems will triangulate it and link it to a parent path. The attribution might not be immediate. Streams mix and evolve. Only coherent timing and chemistry can settle the question. Spectra of bright meteors can reveal elemental fingerprints. If those fingerprints differ from common sources and match a family that was seen in the visitor's coma, the case strengthens. This is detective work conducted in slow motion. The chain reaction also has a policy face. Planetary defense budgets depend on clear narratives. A dramatic near-miss funds a year. A patient argument about resonant lanes and thermal drifts funds a decade. The responsible path is to explain that long-tail risks are real, even when they are hard to feel. It is not fear. It is maintenance of awareness across political cycles. The same instruments that would notice an atlas-derived trickle are the instruments that catch unrelated hazards when they appear. Investment in sky surveys and catalogue upkeep pays dividends, regardless of what this specific visitor leaves behind. It is also honest to list the counterpoints. Many interstellar fragments will not be captured at all. Their speeds and directions keep them unbound and gone. Even if a fraction is captured, the distribution of sizes may favor tiny grains that fall below the energy levels that cause concern. Earth's atmosphere is a thick cushion that converts most of the incoming population into light. The absolute number of additional fireballs would likely be small relative to background. For satellites in Earth orbit, operators already manage micrometeoroid risk through shielding and design practices. A slight increase in flux becomes a planning number, not a crisis. The correct posture, then, is surveillance without drama. Track the parent object as it departs to refine models of where any daughters could roam. Continue routine bolide and meteor surveys and cross-reference radiants that repeat on unusual dates. Task spectrographs to look for chemical patterns that match known features from the coma. Share the data widely so that patterns can emerge across instruments and continents. If nothing special appears, the result is still a stronger network that will be in place for the next visitor. If something does appear, the response will be measured. Update risk maps. Adjust satellite shielding and operations for a season if needed. Inform aviation and civil agencies using calm language that sustains trust. Known versus unknown remains the anchor. We know the mechanisms that deliver small bodies to new orbits over time. We know that resonances and thermal drifts can accumulate tiny changes into noticeable meetings. We do not know whether this specific encounter has seeded paths that matter for Earth. We know how to watch without waiting for spectacle. In the next part, we turn to the star at the center. We will examine how a lively ion tail might interact with solar wind and magnetic fields, what the boundaries of plausibility are, and where speculation should wear a clear label. Stand at the boundary, where a comet's breath meets the wind from the Sunday. The solar wind is a river of charged particles that carries magnetic fields wrapped into a spiral by solar rotation. A vigorous comet carves a pocket in this river. Gas escapes from the nucleus, sunlight strips electrons, and an ion tail forms that points away from the Sunday. The tail is not a ribbon, it is a changing volume with currents and waves. When that volume becomes large and structured, it can disturb the magnetic patterns of the wind that flows through it. The question is how far that disturbance travels, how strong it becomes, and whether it can matter for Mars during this pass. Begin with what is established. Comets build magnetized envelopes known as comaes that interact with the solar wind through a process called mass loading. Neutral atoms from the coma become ions, the wind picks them up, and the added mass slows the flow and bends magnetic field lines. A bow shock can form upstream, a magnetic pileup can build near the nucleus, and waves can propagate along field lines. Spacecraft have flown through such structures and recorded clear signatures. Most of the time, these effects are local to the comet and fade with distance. The scale of influence depends on outgassing rate, solar wind conditions, and geometry. Far from the Sun, even a strong emitter creates a modest obstacle in a vast flow. Now place Mars downstream of this interaction region. For coupling to matter at planetary scales, several conditions must align. The cometary ion population must be large. The direction of the solar wind must steer disturbed fields toward the planet. The background solar wind must be in a state that allows waves to grow rather than be damped. Even when these conditions hold, the result at Mars is expected to be subtle. The planet has no global magnetic shield, so changes in the interplanetary field can map more directly into its ionosphere. That mapping shows up as shifts in the altitude and shape of current systems, changes in the way charged particles precipitate, and variations in how radio waves travel. A practical signature would be a temporary rise in auroral activity and a short increase in radio noise at specific frequencies that instruments monitor. There is a tempting line of speculation that a comet could act as a trigger for a larger solar disturbance. One possibility is that a dense ion tail could seed instabilities in the solar wind that later grow into waves that affect a wider region. A competing view suggests that the solar wind is already turbulent and that the tail is a small perturbation in a noisy medium, one that is quickly mixed and forgotten. Evidence is limited for any strong remote consequence. Known observations favor local effects near the comet, with planetary responses that are modest and short-lived. It remains uncertain whether any coherent structure from the tail could persist long enough and travel far enough to amplify a space weather event that would not have occurred otherwise. The Sun itself provides larger sources of disturbance. Coronal mass ejections and high-speed streams from coronal holes can dominate the near-planetary environment for days. If such a solar event arrives near the time of the cometary pass, disentangling contributions becomes difficult. The sensible approach is to assume that the Sun sets the main stage and the comet can add local texture along specific field lines. Instruments at Mars would then look for coincident timing between changes in the interplanetary magnetic field, variations in ionospheric profiles, and any visual aurora detected by orbiting cameras. If the timeline shows a small modulation that aligns with the modeled passage of the tail through the relevant sector, the case for minor coupling is strengthened. If not, solar drivers explain the scene without help. Energy arguments keep expectations in check. The power carried by major solar storms dwarfs the energy associated with mass loading by a single comet at this distance. The comet can shape a local pocket, but it cannot redirect the river. This does not make the science uninteresting. It makes the signatures delicate. Researchers care about these delicate signatures because they reveal how charged particle populations are exchanged between a comet and the ambient wind, and how a weakly shielded planet like Mars responds to small but timed changes in its electromagnetic environment. What would operators notice if the coupling is real but minor? First, an uptick in auroral emissions near crustal magnetic anomalies recorded by ultraviolet or visible images. Second, brief increases in the variability of radio occultation profiles that map the ionosphere. Third, noise bursts in instruments that count energetic particles. Fourth, small changes in the rate at which orbiters experience drag during low passes if the upper atmosphere warms or cools by a few Kelvin as a result of altered energy deposition. None of these would force a change in mission design. All of them would end up in post-event reports that improve models. Counterpoints deserve equal space. The comet may pass without any measurable coupling at Mars. The solar wind is variable on its own, and this variability often swamps weaker inputs. The ionosphere can wobble for reasons unrelated to comets, including dust lifting that changes heating from below. Spacecraft can enter safe modes because of sun angle constraints without any external disturbance. Good analysis resists the urge to blame the visitor for every blip during a week that is already hard to observe. There is a middle path between dismissal and hype. Treat the ion tail as a traveling laboratory. Its ions are tracers injected into a flow we wish to understand. If Mars samples even a ripple from that laboratory, researchers get a controlled perturbation that is valuable for theory. If Mars sees nothing, that null result still tightens limits on how strong coupling must be before it shows up against background. Either outcome advances knowledge. Known versus unknown remains the compass. We know how comet tails form and how mass loading works. We know Mars reacts measurably to shifts in the interplanetary magnetic field. We do not know whether this particular tail will be large and organized enough to leave a clear fingerprint at Mars, given the distance and the timing. In the next part, we step out of the physics lab and into the storyline of outcomes. We will hold two pictures side by side, one where a fragment finds Mars and one where the sky stays quiet. And we will draw lessons that apply in both cases. Hold two scenes in parallel, like frames on an editing timeline. In one, a fragment breaks free at the wrong hour, crosses a thin corridor, and meets Mars with speeds that turn rock to vapor. A crater blooms, a shockwave climbs the sky, and orbiters blink as their sensors swim through charged debris. In the other, the visitor glides past like a quiet ship on a distant sea. Mars rolls on, instruments hum at their usual cadence, and the story ends with careful papers rather than urgent briefings. Between these scenes sits the narrow shelf where honest risk lives. The task is to learn from both futures without being captured by either. Begin with the loud version. An impact by a fragment, tens to hundreds of meters wide, would excavate a hole measured in kilometers and loft dust and vapor into altitudes that capture sunlight and reroute energy for months. The atmosphere would darken in regions downwind, solar power would dip, radio links would find more noise in paths that skim the limb, engineers would do what they have trained to do. They would shift spacecraft into power-saving modes, retime downlinks, and favor instruments that ride comfortably in messy electromagnetic conditions. Scientists would switch from long-term campaigns to triage. They would track the plume, map the dust, and watch the ionosphere for recovery. The public would see fewer pictures and more charts. There would be headlines, and then a long quiet as analysis replaced spectacle. What would make that scene more than a dramatic interlude is persistence. If the plume seeded a new belt of fine particles that aligned with busy orbital paths, that belt could become a seasonal nuisance. If dust settled on panels across a swath of the surface, rovers would live on thinner margins. If the upper atmosphere cooled or warmed by a few Kelvin for weeks, aerobraking campaigns would revise their models. None of this turns Mars into a forbidden zone. It turns a routine set of tasks into a series of careful steps that take longer. The lasting gain would be knowledge. Researchers would hold a unique dataset on how a thin atmosphere responds to a timed strike and how a weakly shielded planet processes energy injected from above. Now let the quiet version play. The visitor sheds nothing significant near the critical window. Its tail fans in expected ways. Mars passes under a sky that is only slightly more busy than usual. Orbiters report typical noise and nominal power. Surface assets go about their work. Astronomers collect spectra and light curves that feed models of an unusual but not misbehaving body. The weeks after closest approach bring a trickle of results that are precise rather than thrilling. Papers refine the gas mix in the coma, Trajectory solutions narrow uncertainties on non-gravitational forces. Upper atmosphere profiles during the pass show small changes that fit within seasonal ranges. The public moves on, the teams do not. They add one more controlled case to a library that will guide interpretation the next time geometry is less friendly. If this second future arrives, was the caution wasted? No. The exercise of tracing plausible branches sharpens decision-making. It teaches teams to separate instrument quirks from environmental signatures. It tests how communication plans handle observation gaps without feeding rumor. It reminds audiences that space often speaks in whispers, and that hearing those whispers requires patience. Quiet outcomes do not erase the possibility space. They prune it. They tell us where not to look next time. The two frames also share ethical questions. What do agencies say when a visibility gap coincides with a period of concern? How do they keep trust while not overinterpreting early data? The answer in both futures is transparency about confidence. State what is measured, what is inferred, and what remains unknown. Name the next observation that will move an item across the line. If a rover goes silent for a day in the loud future, explain geometry and recovery steps rather than amplifying fear. If a week passes with nothing unusual in the quiet future, explain why that null result is still science. Trust grows when method is visible. There is a human lesson wrapped in the editing metaphor. People crave closure. A loud future offers it quickly. A quiet future denies it. The truth of planetary risk often sits between. The most common consequences are partial. A link that drops, then returns. A detector that saturates, then recovers. A haze that steals a few % of sunlight and then thins. These partials are easy to dismiss and easy to overclaim. The discipline is to treat partials as data points that accumulate. 10 small deviations can matter more than one dramatic event if they teach the same physics with less cost. Each frame also carries a path to improvement. After a loud week, teams would propose better shielding for exposed optics, more robust star tracker logic for streaky fields, and new schedules for crossing dusty plains. After a quiet week, teams would still have work to do. They would propose improved coordination of occultations during conjunction, more stable calibration sequences for trace gas spectrometers, and clearer public dashboards that display the state of Mars networks without the need for interpretation by rumor. Both futures justify better tools. Counterpoints keep us honest. A fragment of the required size remains unlikely to find Mars from this geometry. A perfectly quiet pass remains unlikely. 2. Because the environment is never static. The real sky will land somewhere in the middle. A few hiccups, a few clean successes, a handful of plots that become reference figures in future textbooks. The value of thinking in two frames is not to pick a winner. It is to train attention across a range. When the next visitor comes with a different speed or inclination, the habit of holding parallel scenes will be ready. We restate the through line. The stake is not only whether Mars suffers a blow, it is whether we can read weak signals during a period when cameras squint and radios hiss. Loud or quiet, the payoff is a smarter community that speaks clearly about risk without borrowing heat from fiction. In the next part, we turn from futures to forensics. We will lay out how teams will reconstruct whatever happened using the data they have, what limits those reconstructions face, and how uncertainty is reported when memory must stand in for direct sight. When the sky clears and Mars moves out of solar glare, the work becomes reconstruction. Teams assemble a mosaic of partial views and indirect measurements. The goal is not to replay the encounter like a film. The goal is to build a chain of inference that is honest about confidence at every link. Think of it as a layered autopsy on a living system. Each layer tells a piece of the story, and only when they are stacked do patterns become clear. First come the ephemerides. Astrometric stations on Earth and in space add new positions for the visitor as it recedes. Those points refine the gravity-only path and the small non-gravitational accelerations from outgassing. If the object shed mass near closest approach, the spin state and jet geometry may have changed. That change leaves a trace in the fit. A residual that used to be random becomes systematic. The center of light can wander relative to the center of mass if the coma brightened asymmetrically. Analysts separate those effects with models that have been tested on many comets. The result is a revised trajectory and a tentative map of activity episodes. In parallel, Mars orbiters deliver delayed payloads. Radio occultations provide vertical profiles of electron density and neutral density. By comparing profiles from the week before and the weeks after, teams look for coherent offsets in layer heights and peak values. A consistent rise or dip across multiple local times hints at a real change in energy input or composition. A scatter of differences that refuses to align with geometry points to ordinary variability. The distinction is statistical, which is why large sample sizes matter. A single beautiful profile can inspire a story. A suite of plain profiles writes the real report. Images contribute the context that the public recognizes. Wide-field cameras search for high-altitude hazes or detached layers that were not present in baseline climatologies. Narrow field instruments revisit regions where regional storms sometimes ignite. If dust activity increased during the window of concern, surface contrasts and limb brightness should carry the mark. Teams build difference images with care, since changing sun angle and viewing geometry can fool the eye. Positive findings require matching signatures in thermal data or in dust optical depth estimates from independent instruments. A picture alone is never a verdict. Energetic particle detectors and magnetometers add the space weather chapter. If the ion tail brushed field lines connected to Mars, instruments may record short-lived changes in particle flux and field orientation. The forensics compares timing across platforms. A shift that rolls through altitudes in the right order is more credible than a spike seen on a single bus. The analysis filters out known solar drivers using recordings from monitors upstream in the solar wind. If a coronal mass ejection passed near the same hours, that driver explains most of the variance. Any residual that correlates with the modeled, the geometry of the tail earns a cautious footnote in the summary. Surface assets often provide the cleanest constraints, precisely because they are slow and local. Meteorology packages report pressure, temperature, and optical opacity on tight schedules. A slight and sudden change in opacity near dawn and dusk can indicate lofted dust. A pressure field that wobbles in sync across two sites hundreds of kilometers apart can indicate a regional wave. If such features line up with the arrival of a distant disturbance in the upper atmosphere, the case for a weak coupling grows. If they do not, the safer interpretation is that local weather dominated the scene. The humility to choose the boring explanation is a hallmark of good forensics. Laboratories on Earth join the analysis with spectra that were obtained before and after the pass. High-resolution measurements of the coma reveal bands of carbon dioxide, water, carbon monoxide, and minor species. If a change in band ratios occurred near closest approach, it can indicate a new vent or a change in grain size in the dust that carries fluorescent species. Those details feed the dynamical models that predicted fragment release. They also anchor any claims about exotic chemistry. A claimed anomaly in the Martian ionosphere that lacks a plausible source in the coma chemistry should be treated with skepticism until an alternative mechanism is proposed. The limits of reconstruction are as important as the findings. Solar conjunction introduces data gaps that no clever analysis can erase. Some orbits did not downlink. Some cameras did not point. Some ground stations faced the sun and went silent by design. Good reports draw boxes around those blank hours. They do not smear confidence across the gap. They also report sensitivity. If instruments could only have seen a change larger than a given threshold, the absence of a detection is not a statement that nothing happened. It is a statement that nothing above that threshold happened. Uncertainty reporting is not a ritual. It is an ethical choice that shapes public memory. Each figure in a final paper should carry bars or envelopes that reflect both statistical scatter and systematic flaws. Each narrative sentence should signal the tier of confidence. Words like detect, suggest, and remain consistent with do different jobs. Analysts should choose them with care. When a headline writer later compresses a paragraph into a caption, the spirit of that discipline survives. Forensics also includes the negative space of rumors. If a past looked quiet, and yet social media filled with claims of outages and cover stories, communication teams can publish timelines of contact with vehicles and of instrument states through the gap. A table that lists pass windows, received volumes, and safe mode entries is not exciting. It is a disinfectant. It helps audiences learn the normal rhythms of deep space operations so that the next gap does not feed the same loop. The last step in reconstruction is synthesis. Different teams bring their strands to a common workshop. The best workshops end with a map that aligns time on one axis and altitude on another. Each instrument marks its signatures on the grid. If a faint chain of cause and effect emerges, the community has earned a result. If the grid looks like static, that is also a result. It means the visitor passed without leaving a clear trace at Mars. Either way, the community gained a better feel for its tools and its blind spots. We keep the through line as we close this part. The value of the encounter is not only in what it did or did not do, but in what the reconstruction teaches about reading small signals during awkward geometry. In the next part, we examine how those small signals play in the public square. We will trace how gaps invite narratives, how to speak plainly about risk without feeding anxiety, and how to protect attention for the science that takes time. Silence arrives not as a single event, but as a sequence of absent things, a daily image that does not post, a schedule that slips, a technical note that uses language careful enough to feel evasive to anyone outside the room. During a close pass that coincides with poor geometry, such gaps are guaranteed by physics, not by policy. Yet audiences do not live inside mission timing charts. They live inside feeds that reward novelty and speed. The result is an information vacuum, shaped by orbital mechanics and filled by human psychology. If we want better outcomes, we must design communication with the same care we design star trackers. Begin with expectations. Many viewers expect space events to behave like sports highlights, dramatic plays unfolding in real time with multiple camera angles. Deep space events are more like weather recorded by instruments that need time to be understood. During conjunction, even those instruments must wait. If teams say nothing, speculation sells a story where nothing is known and everything is possible. If teams speak too early, they can lock in a narrative that data will later contradict. The sweet spot lies in structured updates that state what is certain, what is provisional, and what next measurements are coming with their dates. This format does not remove anxiety, it gives anxiety a calendar. Language matters. Words like anomaly and contingency carry technical meanings that are easily misread. Call a safe mode a protective pause. Call a missed pass a geometry outage. Keep verbs active and specific. A sentence that says, "The orbiter is healthy," and conserves power while awaiting the next scheduled contact conveys more than a phrase about temporary issues. Precision without jargon is not pandering. It is engineering translated for people who care. Visuals matter as much as words. A simple timeline graphic that shows contact windows and expected blackouts turns rumor into weather. If a window was missed, the bar stays empty. If the next bar is in 2 hours, the audience knows when to look again. Add a second line that marks the visitor's distance and phase. Add a third that flags known solar activity levels from upstream monitors. 3 lines, updated on a predictable cadence, outperform paragraphs of institutional prose. They also reduce the temptation to fill the void with imaginative but incorrect maps and charts. The vacuum has known tenets. One is the idea of cover-ups. Another is the idea that lack of images implies disaster. The antidote is not sarcasm, it is receipts. Publish a contact log with timestamps and receive data volumes. Publish a list of instruments that were on or off, and why. These are not secrets. They are the daily bread of mission control. Bringing them into the open turns a gap into a ledger. Audiences who want to believe a darker story will not be swayed by any one table. Audiences who are undecided will remember that the teams who fly these machines also show their work. There is also the problem of scale. A sentence that mentions charged particles and radio noise can be reprinted as technology at risk. A sentence that mentions organics can be rewritten as life discovered or life threatened. The fix is to pair scale with every risk description. If ionospheric variability rises, explain that the expected effect is a wobble in a radio carrier, not a lost spacecraft. If trace gases are discussed, explain that organics describes a class of molecules, not living organisms. Repetition helps. So does placing a counterpoint beside each dramatic clause. If we talk about dust, we also talk about the thinness of the air and the routine nature of power management on modern craft. Speed is a trap for both sides. Social media accelerates claims. Institutions can overcorrect by moving too slowly. A workable compromise is the tiered update. A short and frequent status, written in plain language, says what changed in the last 6 hours. A longer, daily brief adds context with charts that engineers already use. A weekly technical note dives into methods for those who want to learn more. Each tier links to the next. Each carries a timestamp and the name of the responsible team. This cadence makes it harder for rumor to claim the mantle of the only voice in the room. The analyst model helps here. Treat claims as hypotheses. For any viral post that asserts a crater or an outage, list what data would confirm or falsify the claim, and when that data will exist. Invite the public to wait with you for that test. When the test arrives, show the result, even if it is visually unexciting. This practice turns skepticism into a shared process, rather than a duel of assertions. Creators and journalists have a special role. The most helpful pieces during a visibility gap do not add color to speculation. They teach how deep space operations work. They show the relay chain from orbiter to Earth. They explain why antennas avoid the sun and why safe modes are signs of health, not panic. They explain that a null result can be as valuable as a dramatic one because it narrows models and trains procedures. Audiences can handle this nuance if it is delivered with rhythm and clarity. Finally, there is the question of trust after the fact. If the past proves quiet, some viewers will feel that their attention was borrowed for nothing. The best response is to pay that attention back, with clear summaries of what was learned and what will change. Show a before and after of the models that predict ionospheric behavior. Show an update to the playbook for operating during conjunction. Show a small improvement in a star tracker algorithm or in a dust forecast. These are modest returns, yet they stack across missions into a culture that values learning over spectacle. We restate the through line. The cosmos rarely gives us dramatic closure on demand. During a pass, we cannot watch cleanly. The choice is between rumor and method. Method wins if we make the process visible, if we speak simply about scale, and if we give people a clock to watch. In the next part, we step into the policy room. We will ask, who decides what to share and when, how law and ethics shape disclosures during uncertain events, and what standards keep caution from turning into secrecy. Policy becomes visible when physics creates silence. During an encounter that overlaps a visibility gap, decisions about what to say and when to say it move from back rooms to front pages. The tension is familiar. Agencies owe the public accuracy and context. The public wants immediacy and certainty. Law, ethics, and institutional culture sit between those wants and those duties. If we design policy with the same clarity we ask from science, a quiet week can still strengthen trust. Begin with the simple frame of obligations. Space agencies are funded to explore, to protect assets, and to inform. Most operate under statutes that require timely disclosure of significant anomalies and hazards. Timely does not mean instant. It means fast enough to enable reasonable action by partners and by the public. Action in deep space often looks like waiting for the next pass, which means that a careful hour beats a careless minute. The first policy choice is to prefer information that can survive scrutiny over updates that satisfy a clock. That choice must be explicit so that staff are protected when they choose caution. Next comes the grading of information. Not every blip deserves a bulletin. Policy should sort events into tiers that map to clear publication rules. A protective safe mode with healthy power and thermals warrants a short status within a known window. A suspected environment-driven disturbance that repeats across platforms warrants a longer technical note with signatures and times. A confirmed loss of an asset warrants a full briefing led by mission management. These tiers are not theatre, they are governance. They prevent over-notification that numbs audiences and under-notification that breeds suspicion. Coordination across agencies raises the stakes. Mars is a shared theatre. One team may own a spacecraft, another team may provide relay support. A third may run a deep space network station that carried the critical pass. Policy must define who speaks first and who echoes. The rule that preserves coherence is source first. The flight project reports the state of its vehicle. The network reports contact quality. The science team reports interpretation. A central account stitches the story with links. This avoids the fog that forms when a support service announces a symptom before the mission announces the cause. It also assigns responsibility so that no one is punished for staying in their lane. Classification and security sometimes enter the room even when the topic is science. frequency allocations, spacecraft fault protection logic, and ground network capabilities can be sensitive. The duty to inform still applies. Policy should force a public version of any sensitive item that carries public impact. If a pass failed because a given frequency was noisy, a redacted but meaningful description is possible. If a recovery step took time because of a security protocol, a generic description can be offered with timestamps. Precision about timing and outcome can coexist with discretion about methods. The refusal to offer any detail fuels speculation more effectively than a careful summary ever could. The question of preprints and peer review is policy dressed as culture. During live events, data flows through analysts who crave the rigor of full review. The public deserves preliminary context. A balance exists. Share plots labeled preliminary with visible axes and units. Add sentences that state confidence and list the tests still to come. Require that preliminary posts name the instruments and the teams so that credit and accountability are clear. This practice respects reviewers without holding basic facts hostage to a schedule that belongs to journals rather than to the public who funded the work. International law adds another layer. Treaties require that states inform others of phenomena that may present danger to space objects or astronauts. The practical translation is that anomaly notices must cross borders quickly. Policy should pre-establish a standard format for such notices that travels through diplomatic and technical channels at once. A one-page template with event, time, assets affected, preliminary cause, and next update, time will do more for safety and trust than any glossy statement after the fact. The template should be public so that citizens see that nations treat space risk as a shared domain rather than a stage for prestige. Ethics is the quiet flaw under all of this. The ethical standard in uncertainty is to minimize harm while maximizing truth. Harm here includes reputational harm from reckless speculation, as well as operational harm from hasty commands. Truth includes stating what is unknown in language that does not imply negligence. A sentence that says, "Analysis continues" is better when paired with the data streams being analyzed and the schedule for decisions. An ethical briefing draws boundaries around speculation and keeps those boundaries intact even when questioned. If a presenter must guess, they say so. If they cannot answer, they say when they can. There is also the question of equity in communication. Communities without ready access to technical feeds or to jargon-heavy sites deserve clarity. Policy can require that every significant update be paired with a plain language version and that both be posted in predictable places. Press briefings can include interpreters and accessible graphics. Time zones matter. If a world audience follows an event, releases should cycle so that no region is always asleep when news is posted. These courtesies cost little and signal a view of space as a global commons. Accountability closes the circle. After the encounter, agencies should publish a communication audit with a simple timeline of events, releases, and decisions. What was said, when it was said, and how confidence changed. Mistakes should be noted without defensiveness. If an early statement was revised, the two versions should be shown side by side with reasons. This practice turns lessons into muscle memory for the next event. It also gives critics fewer shadows to point at. Counterpoints help policy stay grounded. Not every rumor requires a response. Silence is appropriate when speaking would add confusion. Not every dataset can be shared instantly without risking misinterpretation that damages trust. The key is to replace default secrecy with default explanation. If silence is chosen, say why and say when it ends. If preliminary data are withheld, name the validation that must occur first. Clarity about process is a form of truth that keeps a door open while the room is cleaned. We keep the through line clear. Good policy does not promise spectacle or certainty. It promises process, cadence, and candor under pressure. During a week when the sun makes it hard to see Mars, these promises matter as much as any instrument. In the next part, we return to engineering. We will ask what this encounter, loud or quiet, should change in the design of future missions so that the next silence contains less risk and more information. Engineering learns fastest when the sky is uncooperative. Whether this encounter is loud or quiet, it hands future missions a checklist for how to survive and measure during rare disturbances. The target is not invincibility. The target is graceful behavior in noisy conditions, paired with enough sensing to turn noise into science. Designing for the next visitor begins with power, pointing, communication, and environment. It ends with software and culture. Start with power because everything depends on it. Arrays should expect brief dips from haze and from conservative pointing during safe postures. Designers can raise margins with slightly larger panels, or by adding small rechargeable buffers sized for a handful of dark minutes during critical passes. Radioisotope power, where policy allows, removes haze from the top of the risk stack. For solarcraft, dust-tolerant coatings and gentle electrostatic dust removal schemes can buy back percent-level performance without complex mechanisms. None of these additions are glamorous. They buy time for flight computers to think. Pointing follows. Star trackers fail safe if fields streak or glow. Two independent trackers with overlapping but not identical fields help. Onboard logic can gate catalog matching with a transient streak filter that ignores moving features across consecutive frames. Gyro bias estimation can be tuned for longer coast phases, so that a vehicle can hold attitude through a few minutes of messy stars without wasting propellant. Keep the recovery choreography simple. Sun sensors for course lock, then a rehearsed path back to nominal attitude. Simplicity in recovery reduces human workload when geometry is already poor. Communications benefit from layered options and graceful degradation. Equip vehicles with low, medium, and high-gain paths, and practice switching between them automatically when signal quality metrics cross thresholds. Add a narrow telemetry heartbeat that remains on during safe mode, and that carries health bits and a next contact time. On the ground, publish a live clock of expected contacts, so that users who watch can see that silence has a timetable. Consider antennas with slightly wider high-gain beams at modest cost in data rate. Precision is valuable, but survival loves slack. Environment sensing should be considered a core bus function at Mars. A small ion and electron probe tells operators whether the plasma is loud. A dust counter tells them whether the particle flux is rising. A simple ultraviolet photometer at the limb maps high-altitude haze in real time. These add weight and power draw, so trade studies must be honest. The case strengthens when the same sensors also support science during quiet seasons. If environments are measured continuously, safe mode triggers can include context. A vehicle can decide differently when a sensor proves that the sky is calm than when the sensor shows a spike. Charging and materials deserve attention in thin air and variable plasma. Surfaces should present controlled resistivity so that charge bleeds rather than pools. Cables and boards should avoid geometries that invite arcing at expected potentials. Whipple shields are already common. Adding modest shielding in front of vulnerable radiators and star tracker optics can reduce the number of mission-ending bad days. Aperture doors for sensitive cameras can carry a quick, close mode that is used during predicted crossings of dusty plains. The door does not need to be perfect. It only needs to prevent the few impacts that matter. Autonomy is the quiet multiplier. During conjunction, round-trip light time and solar glare slow human loops. Flight software can carry a library of playbooks tied to environment signatures. If dust opacity rises beyond a threshold, the vehicle can reduce loads, adjust attitude to protect arrays, and schedule a retry of a downlink without waiting for ground. If starfields look messy, the vehicle can extend gyro coast with tighter thermal constraints to preserve bias quality. Autonomy should be bounded by simple guards so that surprises do not cascade. The aim is not artificial cleverness. The aim is codified experience. Data handling needs to anticipate intermittent links. Compress instruments with region of interest modes that recognize scenes likely to carry signatures of plasma or dust effects. Store short burst high-rate snapshots for later downlink, rather than streaming long sequences that will be cut mid-pass. When contact returns, send health first, then thumbnails, then science in priority order. On the ground, mirror this order in public dashboards, show green lights for bus health before posting pictures, and teach audiences to watch those lights. Trajectory and corridor planning can fold in dust weather the way Earth missions fold in terrestrial weather. Aerobraking campaigns can keep optional weeks so that crossings of suspected streams can be shifted. Relay orbits can be designed with alternative nodes that allow high-value passes to occur away from predicted dusty longitudes. This demands better nowcasting of Mars dust and better prediction of meteoroid streams. Both improve when many missions share their counts and limb observations. Mission charters can require that basic environment data be shared openly in near real time. Instruments themselves can be hardened against spurious signatures. Detectors can be shielded at edges where streaks enter at grazing angles. Readout schemes can flag transient pixels and rebuild frames without them. Calibration sequences can include quick sanity exposures before long integrations in noisy weeks. These are small habits that prevent bad data from contaminating long baselines. Mass and cost are the counterweights to every proposal. Not every craft can carry every sensor. Not every program can afford every shield. The correct approach is hierarchy. Core buses that expect years at Mars should carry environment sensing and extra margin. Short-lived probes can accept more risk and ride simpler designs. A diverse fleet is healthier than a single strategy applied everywhere. Software development practices matter as much as hardware. Simulators should include disturbance playbacks derived from past events so that teams rehearse recoveries with realistic noise. Fault protection should be tested against ambiguous sensor mixes, not only against clean failures. Telemetry dictionaries should reserve fields for environment context so that analysts do not chase ghosts without the sky on the same page. Post-event drills should write patches that can be flashed quickly when a visitor leaves behind a new rhythm in dust or plasma. Finally, build culture that treats odd weeks as laboratories rather than as embarrassments. Publish bug fixes and algorithm improvements with short notes that credit the problem and the team. Share successful recovery timelines so that others can borrow. Incentivize missions to turn safe mode stories into engineering papers that future designers can cite. Resilience grows when the community moves improvements across projects quickly. We keep the through line clear. The next visitor may arrive when cameras can see clearly or when geometry is cruel. In both cases, the winners will be machines that ride through noise without losing their memory, and teams that convert interruptions into measurements. In the next part, we pivot back to science. We will ask what this encounter tells researchers about small bodies from other stars, and how to frame big hypotheses with disciplined tests so that mystery fuels discovery without outrunning evidence. Science advances fastest when a puzzle is framed so that both answers and null results carry weight. An interstellar visitor is a rare puzzle with many handles. It can be a chemistry lesson, a physics lab for gas and dust dynamics, and a stress test for planetary environments. The temptation is to leap past data into broad claims. The discipline is to stack evidence slowly, so that each claim can hold its weight when the excitement fades. If this encounter is used well, it will leave behind more than anxious headlines. It will leave behind improved methods and a cleaner map of what we do and do not know about bodies that formed around other suns. Begin with composition because composition anchors every other inference. Spectra at infrared and ultraviolet wavelengths carry fingerprints of simple molecules. Carbon dioxide, water, and carbon monoxide define the backbone. Minor species add color. Ratios between these lines change with temperature, with activity level, and with geometry. They also encode clues about formation conditions. A higher than usual fraction of carbon dioxide at large solar distance can imply condensation in a region that was colder or at a pressure unlike our own outer disk. One possibility is that grain growth and ice layering followed a path that is unusual for solar system comets. A competing view suggests that geometry and current activity can mimic such a signal. It remains uncertain until time series across many heliocentric distances are in hand. The good news is that modern telescopes can deliver those series even when the object is faint, provided observers plan patiently. Dust tells a complementary story. Polarization measurements and color slopes in scattered light constrain grain sizes and structures. Fractal clumps scatter differently than compact grains. Porous aggregates favor certain angles. If the visitor sheds dust that is richer in very fine particles than typical comets, that result points to different collisional histories in its birth disk. If the size distribution looks familiar, that similarity suggests that grain physics is universal across disks. Either outcome is a win. What matters is that measurements are tied to the same times as the gas spectra, so that correlations can be drawn between dust, size, and outgassing style. Without simultaneity, dust results drift free of context and can be overinterpreted. Non-gravitational forces provide a dynamic probe of internal structure. Outgassing jets push on a nucleus. The pattern of these pushes across a rotation cycle can change spin states and gently bend the orbit. Astrometry, that resolves these small accelerations over months can back out where activity sits on the surface and whether that activity migrates. A nucleus that changes spin period quickly is likely weak and fractured. A nucleus that keeps a steady period despite bright activity may be more cohesive. Evidence is limited during conjunction. The inference grows stronger once the object exits the glare and tracking resumes. Null detection of non-gravitational acceleration is a result too. It constrains how symmetric the activity must be to hide a push of a given magnitude. Plasma interactions are another laboratory inside the larger laboratory. Pick-up ions in the ion tail provide traces for the solar wind. In situ, measurements are not available near Mars for this object, but remote sensing can sketch the presence of waves and field line draping in broad strokes. Models that fit those patterns can then be used to predict how other interstellar visitors would behave closer to the Sun where measurements might be more direct. The experiment is generative. A quiet pass here seeds better tests in a livelier future case. There is a speculative branch that can be handled responsibly with clear labels. A minority view holds that some brightness variations may carry structured patterns that hint at artificial modulation. Evidence is thin and does not survive ordinary checks against geometry and thermal physics. If a study of light curves proceeds, the correct posture is to treat it like any search for periodicity. Remove known rotation signals, correct for phase angle and viewing geometry. Test for prime sequences and for ratios that do not arise in thermal or jet models. State thresholds clearly. If nothing remains after these steps, report upper limits without rhetoric. The act of looking is not a claim. It is how science closes a door politely. Meteor science offers another channel where patient surveys matter. If future years produce a faint shower that repeats near an unusual solar longitude, cameras and spectrographs can link grains in that shower to the visitor. The mineral fingerprints of ablation light can be compared to coma spectra. The match will never be perfect. It can be persuasive enough to say that a fraction of the stream shares a parentage. This is deep time science, it asks, for long attention spans and for networks that can keep watching when no particular news story is running. Comparative planetology benefits, even if Mars shows nothing unusual. A null at Mars, while a similar visitor perturbs a different planet, later becomes a contrast set. The contrast reveals how magnetic shielding and atmospheric depth change outcomes. A thin Martian ionosphere that shrugs, while a thicker Venusian ionosphere wobbles, would be a sharp lesson. The reverse would be sharper. These cross cases are rarely available. When they do appear, they turn vague models into specific laws. The social side of science gains as well. Interdisciplinary rehearsals build muscle. Dynamicists learn to coordinate with atmospheric modelers and with space weather teams. Communications staff learn to translate preliminary curves without removing the meaning. Students see how a community behaves under uncertainty. The next time a rare visitor arrives, the lanes between groups will be paved. That improves both speed and accuracy. There are counterpoints worth stating so that expectations remain sane. Not every interstellar object will be bright enough for the full menu of measurements. Some will arrive on paths that keep them too far for months. Some will break apart early, leaving only a trace. Funding cycles do not always align with celestial calendars. A telescope upgrade may arrive one season after the object that would have been perfect. The remedy is to build flexible programs that can be triggered by alerts and that can share time across institutions. The system that watches for near-Earth asteroids has already taught this lesson. Interstellar work can borrow its logistics. Known versus unknown is still the backbone. We know how to read basic molecules and dust scattering. We know how to measure small accelerations with good astrometry. We know how to fit models to ion tail interactions with the solar wind. We do not know the diversity of compositions or internal structures across interstellar populations because the sample is small. We do not know which disks produce which signatures. Every careful observation grows that sample and narrows those questions. We close this part with a thesis that guides the rest of the script. The science payoff is largest when the community treats a quiet pass as a controlled experiment, and when it treats a loud pass as a measured case study rather than as a spectacle. Either way, the result is a step toward a catalogue of rules for visitors from other suns. In the next part, we return to narrative pressure. We will tally real risks without sensationalism, and we will state what would actually change day to day for Mars missions and for people on Earth if the worst plausible non-impact outcomes stack together. A ledger of risk is not a prophecy. It is a calendar of small frictions that add up. If this encounter leaves a fingerprint without a direct hit, what shifts in the daily life of Mars missions and what stays the same? The image to hold is a control room, where the clocks still run, the screens still blink, and the coffee still cools next to checklists. The difference is tempo. Tasks move a beat slower. Margins are spent more often. A few plans slide right on the schedule. None of this makes a headline. It still matters. Start with passes. Relay windows are the pulses that move data and commands between worlds. A modestly noisier ionosphere turns. Crisp passes into passes with a wobble. A link might lock a minute late, fall to a lower data rate for 10 minutes, then recover in time to flush the buffer. Flight teams respond by padding each plan with a small reserve. They send high-value commands earlier in the pass. They request a second window later in the day to cover what might be missed. The day feels longer, even though the clock is the same. Power budgets bend next. A thin haze or a slightly higher dust index can shave a few percent from solar input. Engineers react by trimming. Appetites for hours when arrays are at poorer angles. Cameras that like long exposures are given shorter sequences. Instruments that warm their detectors are cycled with longer rests. The rover that takes a panoramic shot every afternoon might take it every other afternoon until the haze thins. The orbiter that runs 3 science modes per orbit might run 2 and save the third for a cleaner geometry. These choices keep buses healthy while converting a tiny environmental change into a measurable impact on cadence. Navigation adjusts in the background. If upper air densities drift a little because high layers warmed or cooled by a few Kelvin, the drag models that guide low-altitude skims take a handful of extra iterations to converge. Navigators will expand uncertainty bounds for a week, which means maneuvers are scheduled with slightly larger fuel guards. That cost is small, yet real. Every kilogram of propellant that goes to margin is a kilogram that does not go to a later campaign. Over a long mission, a few such weeks change the shape of an extended phase by a fraction. Fractions are the currency of longevity. Star tracker hygiene becomes a quiet ritual. Streaks and glows appear more often in the field. The onboard logic handles most of them, yet operators adopt cleaner habits. They avoid long stares through longitudes where streak counts are highest. They schedule short recalibration looks toward cleaner patches of sky. They rehearse a coast through a few minutes of confusion, so that the bus does not overreact. These are light touches that remove tension for everyone in the loop. Instrument teams shift their own rhythms. A spectrometer that is sensitive to charged particles adds short guard frames to check for transient flashes before longer science exposures. A camera that counts fine dust near the limb turns on for a few minutes more often to watch for changes in high-altitude layers. A particle sensor that is usually secondary is brought up more often to give context for any odd signatures in other data. The teams publish more quick looks in internal channels so that different missions can compare notes within a day rather than after a week. This collective tempo is how small signatures become shared knowledge instead of isolated curiosities. Ground networks feel the load gently. If more passes are requested to hedge against wobbles, schedulers at deep space antennas shuffle slots with more care. 1 or 2 windows that would have gone to a routine downlink are given to the mission working through a noisy hour. This is not a crisis. It is a reminder that coordination is a living skill. The reward is a community that can absorb one awkward week without pushing anyone to the edge of their plans. Public updates follow a steadier ladder. Status notes arrive on a fixed cadence that says what changed and what did not. A visible contact timeline reminds viewers when the next window opens. If a safe mode occurs, it is labeled a protective pause and followed by a time-bound plan for recovery that lists the next 3 steps. The wording pairs scale with event. A missed pass is a missed pass, not a sign of cascading failure. A detection of a trace molecule is a detection, not a declaration of origin. Audiences do not need drama to stay. They need a clock, a map, and a tone that treats them as partners. Science yields get trimmed slightly but not broken. Long campaigns that rely on stable calibration insert more cross-checks. Time series keep the same total hours by spreading over more days. Opportunistic observations give way to planned sequences that carry higher value per minute. The effect is a rebalanced portfolio. Fewer experiments run on a given day, yet the experiments that run are chosen to survive and even exploit the environment that exists. A dust index that rises becomes a variable in a study rather than a nuisance that forces a cancel. Risk to hardware stays in perspective. The cumulative chance of a micro impact that matters rises by a small fraction if a thin stream crosses an orbital plane. Teams respond by changing attitude during known crossings and by closing protective doors on the most vulnerable optics for a few minutes. The same is true for static. If charging monitors read a little higher, the bus will bleed charge more often and avoid certain pointing angles. These behaviors are baked into design. The ledger notes more entries this week, then fewer the next. What about people on Earth? The day-to-day for the public does not change. No lights flicker. No phones lose signal because of a comet millions of kilometers from Mars. The only human-level shifts are in attention and in learning. If communication is done well, the week becomes a class in how exploration handles noise with calm practices. If communication is done poorly, rumor fills the vacuum and leaves a residue of distrust. The ledger reminds us that trust is the only system without redundancy. Counterpoints keep the ledger honest. A quiet pass may produce none of these frictions. A louder pass may produce a handful more. The range is narrow because the geometry is forgiving. The important point is that even within that narrow band, details matter. Teams that prepared with small sensors and clear playbooks will log the week as a nuisance with a bonus of data. Teams that did not prepare will spend the same week working harder for less. We keep the through line. The realistic risk ledger is not a page of disasters. It is a record of modest adjustments in passes, power, pointing, and patience. It is also a plan for converting a noisy sky into science without breaking cadence. In the next part, we return to story. We will write an alternate day when a fragment does strike, and we will show how the same discipline holds even when the sky is loud. Set the clock to a day that splits the difference between spectacle and science. The fragment is not a mountain. It is a block the size of a city square, dense and fast. A sliver from a body that wandered far from any Sunday. Its path threads a shallow corridor and meets Mars at an angle that turns energy into heat with ruthless efficiency. For a few heartbeats, the sky over the impact site brightens as if a second dawn rose from the ground. The flash is brief, the physics is not. Rock liquefies, then vaporizes. A cavity opens and rebounds, then freezes into a scar that will mock our maps for ages. Orbiters see it first, then they do not see anything at all. Star trackers fill with streaks and alarms. Magnetometers report a lurch as charged debris rushes upward and outward. Radios that were clean become grainy as the ionosphere shakes like a drumhead. Fault protection logic does what it was born to do. It calls for a protective pause. Instruments power down in a sequence learned during countless simulations. Solar arrays twist to surviving angles that favor power and safe temperatures. High-gain dishes step away from perfect pointing and accept lower data rates. In control rooms on Earth, the plots flatten, no one shouts. The cadence slows and grows precise. On the surface, the shock runs like a wave along old valley floors. Dust jumps, fines saltate and stick to faces that were already dusty. Seismometers wake happily even as their operators grimace. Pressure sensors catch a passing pulse that speaks the language of a distant hammer blow. The air does not burn. It thins and thickens as a wall of heated gas climbs and spreads. Sunlight dims across a wide sector as a slender umbrella of dust blooms at altitude. What follows is not a night. It is a long afternoon that never quite finds its light. Science pivots without ceremony. Cameras that would make pretty horizons are turned to the limb to find detached layers and to count their rise. Spectrometers that study trace gases look upward to measure how energy deposition has changed photochemistry. Orbital imagers set their mosaics aside and try for quick looks at the new scar to estimate ejector patterns and to infer the strength of the target rocks. Particle counters learn a dance of silence and song because the environment is punctuated now. Quiet minutes follow loud seconds as clumps of charged grains pass by. Recovery is a postcard sent in many small messages. The first are health bits from vehicles that did not lose their orientation. Then arrive short packets that confirm that batteries are charged and temperatures are safe. Then a trickle of thumbnails that show nothing dramatic. Dark fields, star streaks, limb arcs that are slightly brighter than last week. Teams refine their expectations. They stop asking for a flood of data. They ask for the next breadcrumb and the next. When a rover finally whispers that its wheels are dustier and that its sky is dimmer by a measurable fraction, the story begins to take a shape. The regional weather responds the way a thin atmosphere must. Where heated columns punch, air aloft spreads and cools. The temperature step alters stability and triggers waves that ride along old canyon rims. Dust seeded at the impact climbs and then migrates downwind. It acts as both mirror and blanket. It reflects sunlight to space while trapping infrared from below. The net is a day cooled by a few degrees in some places and warmed slightly in others. The differences drive eddies that add more dust. Models that scholars built for seasonal storms now become living tools. They take fresh numbers from orbit and from the ground, and they predict where the next patch of thickened sky will drift. Engineering choices carry consequences, and now they show their value. A door that shields a fragile imager is closed during the worst crossings. A radiator that faces forward is rotated a few degrees to deflect the densest flow. A link schedule that was written for a clean day is torn up and rewritten for passes that begin late and end early. The Deep Space Network shuffles windows to allow a second chance for the presser, the vehicle that missed its first. Every decision trades a few minutes here for a few minutes there. The sum is survival through a rough week. Public information flows in a measured stream. The first statement says that an impact has occurred and that spacecraft have entered protective postures. It lists what is known. A bright flash, a new feature consistent with a crater, and a rise in high-altitude opacity near the limb. It lists what is not known. The exact size of the crater, the degree of dust loading globally, and the state of specific instruments that are still in safe mode. The second statement arrives after the first cycle of contacts. It shows a map with a box drawn honestly large. It extends sympathy for the loss of a day of images and replaces drama with the promise of method. When early pictures of the scar arrive, they carry a scale bar and captions that explain what ejector patterns reveal about angles and speeds. The art serves the analysis rather than the reverse. There are low points. A sensor saturates and cannot be nursed back. A pass that was expected to carry crucial spectra turns to static before the handoff completes. A rover shuts its mast camera for an entire sol, and the team can only watch housekeeping numbers trickle in. Someone writes a sentence for a press note that strains the boundary between precision and comfort, and then rewrites it with better verbs. These moments reveal the character of the program. The teams that trained for uncertainty bend and do not break. There are wins that do not look like wins. A string of radio occultations that all show the same modest shift in electron peak altitude. A sequence of thermal profiles that prove the upper atmosphere warmed by only a few Kelvin. A map of optical depth that rises near the limb then falls predictably. These are quiet proofs that the planet remains within the envelope that designers considered. The day Mars died is a headline that age will laugh at. The day Mars was complicated is closer to truth. Counterpoints belong in the same frame. The crater is real, but it is only one among thousands. The dust is thick locally but declines quickly with distance. The ionosphere stirs but does not collapse. If we speak with respect for scale, we make room for the people who will fly next month under the same sky. Their craft will need attention and patience. They will not need new fears. Close with the lesson that is old. Impact physics is fast, recovery is slow, and meaning arrives in steps. If Mars takes a hit during a week when our eyes are half closed by the sun, the right response is to keep cadence, to retrieve what can be retrieved, and to write a clear first chapter. The later chapters will refine the picture. The monitors will stop hissing. The stars will look like stars again. The scar will stay. It will teach, quietly, every time a camera passes overhead. Planetary defense lives or dies by the difference between panic and patience. A close pass near Mars, that is mostly quiet, teaches the quiet virtues that keep a civilization safe. The lessons are not cinematic. They are procedural, statistical, and budgetary. They live in how surveys are funded year after year, in how international notice templates are written, and in how engineers are allowed to test fault protection against ugly edge cases without being told to hurry back to prettier work. If this encounter changes anything on Earth, it should change how we talk about risk that is real and rare. Begin with the cadence of seeing. Detection is the first line of defense, and detection is a habit, not a sprint. Sky surveys that map near Earth, objects, and the wider population of small bodies must keep a metronome pace. The correct response to a quiet encounter is not to cut funds because nothing dramatic happened. It is to stabilize funds so that the next visitor is found earlier, characterized better, and tracked through awkward geometries with enough coverage to avoid rumor-filling gaps. Long horizons require that instruments be upgraded on predictable schedules, that staffing be maintained through calendar lulls, and that pipelines for data become boring in the best possible way. Characterization follows detection. Knowing a path without knowing a nature is only half a defense. Spectroscopy, light curves, and thermal measurements teach density, spin state, and surface behavior. Those traits determine how an object would respond to a deflection attempt. A body that vents strongly will not behave like a monolithic rock when nudged. A body that is porous and weak will fragment under forces that would slide a stronger body intact. Planetary defense plans need these character maps to avoid false confidence. A calm budget buys the patience to collect those maps for many targets, not just the ones that briefly trend. Modeling is the third pillar. Simulations of impacts, atmospheric entry, and deflection must be tuned with real events. A quiet Mars pass is still data. It provides a baseline for how thin atmospheres respond to small injections of energy and particles. It tests the robustness of star tracker logic and link margins when the sky is a little messy. Those engineering lessons fold back into Earth defense because the same buses and sensors will fly on missions that scout hazardous objects. A deflection campaign that launches in a future decade will rely on navigation and communication software that survived weeks like this without drama. International agreements and notice procedures are the paperwork backbone that make technical work matter. A false alarm can harm trust as severely as a missed warning. The lesson from a quiet week is that notices should carry the shape of confidence and the schedule for the next check. A standard format that names the instrument, the observation window, the uncertainty bounds, and the next planned update is better than a breathless alert that says little and spreads far. Calm templates make room for focused alerts when they are truly needed. They also train public and press to read the signals rather than the tone. Education must be treated as defense infrastructure. A public that understands the difference between organics and organisms, between safe mode and failure, between a radio blackout and a lost spacecraft, is harder to panic and easier to mobilize if a real threat appears. The week around this encounter can be used as a teachable case. Museums, classrooms, and newsrooms can show how deep space events are measured and how absence of images does not mean absence of data. This investment pays forward. When an object is found on a path that requires action, fewer days will be lost to explaining basics. Testing and rehearsal deserve a budget line of their own. Planetary defense is not only about launching kinetic impactors or gravity tractors. It is also about rehearsing recovery from glitches during planetary flybys, about practicing coordinated observations during conjunction, and about verifying that communication ladders between agencies work when time zones and languages collide. A quiet week is a gift for such practice. It allows teams to refine procedures without the adrenaline of a true emergency. The results are checklists that read clean and that can be pulled from a shelf at 3 a.m. without confusion. There is a temptation to reframe every rare event as a referendum on grand programs. Resist that urge. A single close pass that was mostly uneventful does not prove that risks are exaggerated. It proves that geometry and physics were kind this time. The correct lesson is humility toward variability. Budgets that surge on fear and collapse on calm will never build the layered systems that reduce risk over decades. Stable funding for surveys, for characterization, for modeling, and for technology demonstrations is the grown-up posture. It is less satisfying in a news cycle. It is more satisfying to historians. Technology demonstrations still matter. A successful test that nudges a harmless target by a measurable amount is the laboratory that enables future decisions. The key is to pair demonstrations with realistic operational constraints. Test guidance and navigation under limited tracking. Test communication through scheduled blackouts. Test deflection scenarios on targets that are rotating, venting, or binary. The more demonstrations match the messy targets the sky provides, the more credible the capability becomes. Counterpoints belong in the ledger. Some argue that resources should focus first on hazards near Earth, rather than on distant events at Mars. The response is that the same tools and habits serve both. Surveys that find interstellar visitors find near-Earth objects. Communication templates that explain a quiet week at Mars will carry a community through a noisy week aimed at Earth. Engineering that keeps a Mars orbiter calm during a dusty hour will keep a scout probe stable as it reconnoiters an asteroid that may one day need a push. The system is one system. Its practice should be continuous. We keep the through line visible. Planetary defense is not a panic button. It is a culture of steady seeing, steady measuring, and steady explaining. A quiet encounter near Mars is a chance to normalize that culture in public view. When the day arrives that a decision must be made quickly, the institutions will be ready, the public will recognize the playbook, and the sky will feel less like an unknowable threat and more like a problem we train to solve. In the next part, we turn to people and story. We will write how explorers, students, and audiences can hold wonder and caution at once, and how to keep curiosity bright when the cosmos refuses to give us easy endings. When the feeds settle and the long week slides into ordinary time, people remain. Engineers return to home routines with notebooks heavier by a few lessons. Students close tabs and keep one eye on a sky that looks the same as yesterday. Viewers who stayed with the story find themselves holding a mix of relief and anticlimax. This is the afterspace of a near event. It needs craft. Without it, curiosity dims or hardens into cynicism. With it, the audience keeps its appetite and its trust. Begin with the simplest act. Tell the whole story cleanly. Give a readable timeline that begins before the encounter and ends after it. Mark the geometry that limited our view. Mark the instruments that did the most work. Mark the real changes that were measured and the limits that held. Pair each claim with a picture or a plot that a patient person can follow. The point is not to dazzle. The point is to show that the method works and that the people who apply it speak in a voice that respects the public. A story that shows its stitching invites the viewer to return next time with less suspicion and more attention. Next, turn data into learning. Build short explainers that use the week's events as anchors. One explains how ionospheres wobble. One explains why star trackers sometimes prefer darkness to too many faint streaks. One explains how dust changes light and heat, even when the air is thin. These pieces do not need to be long, they need to be concrete. They should reuse real numbers from the week rather than generic examples. When a lesson uses the event that the audience watched, it feels earned. When it uses invented scenarios, it feels like a detour. Honor the human work, name the teams, show a few desks with night shifts marked in pen. Show the checklist that carried a vehicle through a protective pause. Show a snippet of code that trims a pointing plan when stars look messy. These glimpses are not sentiment, they are context. Viewers trust systems more when they see the people behind them as careful rather than perfect. Careful people narrate uncertainty as part of the job. Perfect people pretend uncertainty does not exist. The first kind earns patience. The second kind loses it. Invite new hands. A week like this is a recruiting tool if we let it be one. Teachers can adapt plots into classroom labs. Clubs can build small sensors that count meteors or measure sky brightness. Citizen science platforms can host campaigns that compare local meteor counts to predictions from dust models. Young programmers can help build open timelines that harmonize public telemetry from many missions. None of this replaces expertise. It adds long-term attention that strengthens the fabric of watching. When a real risk surfaces in a future year, that fabric will carry more useful eyes. Calibrate wonder. Space serves awe easily. It is also noisy and slow. If wonder is tied only to spectacle, it burns out. If wonder is tied to method, it endures. A short film that opens with 2 seconds of a bright limb, then lingers on the silent hum of a relay dish, then resolves with a plot that shows a small shift, captured by patient instruments, teaches a public rhythm that matches reality. Think of music with quiet measures that make the crescendo honest. One event cannot do this alone. A series can. The afterspace is where the series begins. Set boundaries against hysteria. Misinformation will continue to float. The cure is not to fight every wave. The cure is to keep a stable channel that posts on a schedule. That channel should run a visible corrections log. If an early number moves, show the old value and the new value with the reason. This practice inoculates against the claim that facts are slippery. It also teaches a useful idea. Revision is not failure. Revision is a feature of honest work. Translate to everyday life without stretching. People will ask if they felt any effect on Earth. The answer is no. They will ask if Mars is off limits now. The answer for this pass is no. They will ask if a quiet outcome means the fears were exaggerated. The answer is that prudent preparation is not a mistake when the sky is unpredictable. Use metaphors that respect intelligence. A shield that is never struck was still worth carrying on a road where stones sometimes fall. Art can help the afterspace breathe. Commission a map that overlays the old sky with the new faint traces. Commission prints that show the scar if there is one, with a scale bar that fits on a desk. Commission a sound piece that turns a week of radio noise and passes into a slow pulse. These are not gimmicks. They are memory devices that turn an abstract week into something a person can hold and share. Memory keeps funding honest and keeps apprentices walking in the door. Plan for the next time with public participation. Publish a prep list for how audiences can follow along better. Link to the contact timelines and the dashboards that matter. Explain how to read a dust index and how to know when a safe mode is protective rather than dire. When the next visitor arrives, the community will already know where to look. Rumor will have less room. Note the emotional truth. Some viewers wanted a spectacle, some viewers feared one. Many held both impulses at once. Address that directly. Say that wonder and caution can live together without cancelling one another. Say that a quiet pass is a gift, because it gives us time to improve without paying too much. Say that a loud pass can be endured with the same tools if we keep them sharp. Close with action. What we do next is simple. We keep the surveys fed. We keep instruments healthy. We publish methods that others can use. We test fault protection against messy skies. We write stories that follow the evidence. We keep a public clock that beats through noise. We treat each near event as a rehearsal and each rehearsal as a chance to make the next performance safer and more revealing. We keep the through line in sight. Known and unknown still share the frame. We learned what the instruments could see and what they could not. We learned what rumors want and what audiences deserve. In the next part, we will gather the entire arc into closing speculation and clear takeaways. We will state what shifted in our understanding, what remains unsettled, and how to carry both forward without losing the thread. Hold the frame steady. We began with a simple tension. A rare visitor would pass a familiar world during a week when our view would be poorest. Across that constraint, we laid two rails. The first rail was the storyteller's urgency. The second rail was the analyst's caution. Between them, we walked the line of known and unknown. Now we close without pretending to solve what time has not yet revealed. Begin with the facts that will age well. Interstellar objects do not owe us drama. Most encounters are lessons in patience. Mars remains a thin, aired world that reacts strongly to small inputs in its upper layers and only modestly at the ground. Its moons live on fragile terms set by gravity and by the kind persistence of dust. Our spacecraft are robust enough to ride through days when the sky hisses. Our models are good enough to predict that a pass at tens of millions of kilometers will not rewrite orbits. These are anchors for memory. What then did this story add? It tightened our sense of scale. It showed how an ion tail might trace lines through a river of particles that flows from the Sunday. It taught how dust can serve as courier and catalyst without turning a planet into a different world. It forced a rehearsal of communication in a week when images would be scarce. It asked us to test how well we can keep a clock in public while the cameras blink in and out. That rehearsal matters because the next event will bring its own geometry and its own temptations. One possibility is that the quiet case holds. The visitor leaves a faint chemical and electromagnetic ripple that hides inside seasonal noise. If so, the win is methodological. We will have kept instruments stable through conjunction. We will have shown that null results are valuable when they tighten bounds. We will have improved star, tracker logic, and dust-aware operations. We will have written a better communication ladder that can be climbed again without panic. A quiet case is not a failure, it is a clean control. A competing view suggests that small outbursts or fragment trails may reveal themselves later, as thin streams that cross orbital planes or skies on Earth at new radiant points. If that unfolds, the payoff is a patient one. Surveys will notice a trickle of meteors with unfamiliar spectra. Operators will log a few extra micro-impacts over certain longitudes. Models will link these threads to the visitor and build a story of resonances and thermal drift that move small pieces across years. The effect would be subtle. The lesson would be large. Gravity and sunlight write in slow ink. It remains uncertain whether exotic chemistry from another star will ever complicate life detection on Mars. Evidence is limited, yet it is reasonable to prepare our notebooks. We can choose to archive context with every trace gas reading. We can choose to keep isotope ratios front and center when provenance matters. We can choose to keep planetary protection as a discipline of clarity rather than a mood of fear. These choices cost little and protect the meaning of the hardest measurements. There is a larger moral that folds science and culture together. Spectacle pulls attention, method keeps it. The audience that stays through a week of sparse pictures is an audience that can help build a better public square for space. That square needs clocks, maps, and honest verbs. It needs creators who can translate safe mode into protective pause without draining meaning. It needs journalists who ask what is known now and what measurement is coming next rather than who is hiding what. It needs institutions that publish timelines and corrections without defensiveness. Trust grows when the work looks like work. Takeaways for the missions are plain. Build power and pointing margin for messy skies. Carry small, environment sensors that turn nuisance into data. Practice autonomous playbooks that conserve power and memory without waiting for ground. Share dust counts and limb haze in near real time so that the fleet behaves like a network rather than a set of isolated projects. After the pass, publish an engineering harvest that others can plant in their designs. These are not grand gestures. They are the careful habits that keep exploration resilient. Takeaways for planetary defense are plain as well. Keep surveys fed through quiet years. Keep characterization paired to detection so that paths are joined to nature's. Keep modeling tied to events rather than to headlines. Keep international notice templates short, dated, and clear. The next decision that matters may arrive on a calendar that does not match a news cycle. Prepared systems will not care. For audiences, the compass is simple. Hold wonder and skepticism in the same hand. Ask for evidence and for timelines. Notice when a claim offers scale. Practice waiting for the next pass rather than the next rumor. When asked what happened, answer with form as well as content. We ran a plan. We kept a ledger. We learned a little about how a thin sky and a bright tail talk to each other across a river of particles. We learned more about how people interpret silence. A minority view holds that a message might be hidden in brightness and timing. If such studies proceed, they should carry the most careful labels we use. Tests first, claims later, and likely never in this case. The act of looking is a way to close a door politely. It also honors the curiosity that brought us to this story. We can explore strange ideas without selling them as truth. End with the paradox that started our hook. A coincidence of timing turned a routine pass into a test of our systems and of our patience. That coincidence is the point. We do not choose when the cosmos sends a visitor. We choose how we listen. We choose whether we turn gaps into noise or into clocks. We choose whether we demand spectacle or accept careful progress. The worst case was never only a crater. It was a failure to learn. The best case is a notebook full of methods and a public that knows how to read them. Carry this compass to the next encounter. Keep the through line, known as ballast, unknown as sail, curiosity at the helm, caution as keel. When the sky goes quiet again, and it will, measure the quiet. When the sky speaks, and it will, hear the signal and write it down. That is how a young civilization practices for adulthood among wandering messengers from other suns.